MiniConf. Day one was a lot of fun, and so today we also have a really great lineup. To get us started, there's Hiro with pathfinding algorithms. So I'll let him get started in a sec. Before I get started, before I let him start, there's pizza. Help yourself to that. There's also some water over there and cups. If you have any trash, there's a trash in the back there. So please put your trash away. There's also something, I believe there's also a trash can outside, or a trash bag outside.
Combustibles and cans.
Okay, combustibles and cans. The bathroom is over here. If you just go straight into this room, you'll see it. Yeah, thank you so much for being here. I know it's raining, it's not a great day, so thanks for coming all the way out to Roppongi. And I'll let Hiro get started with pathfinding algorithms. Yay!
Anytime now.
Okay, good afternoon, everyone. I'm going to talk about introduction to pathfinding algorithm. Before we get started, let me say a quick introduction. My name is Hiroyuki Momoi. I'm a full stack software engineer, currently student at Chrysalis. And most of my background is implementing Microsoft infrastructure solution. In the last 2-3 years, I often use Microsoft Azure, Office 365, or 365. And I have most of my experience as a project manager. And I use a Pinbox style and Scrum style. And now I'm currently building a web application. And my passion is develop route navigation solution for virtual users. One of the reasons I decided to switch job to software engineer is I love travel around the world, and I always using some kind of mapping navigation, but oftentimes it doesn't work for me because it's not considering the stairway or elevator or gaps, something like that. So if I build my own some nice application for me, it works for me. So I hope it's not only for me, it's only for the people who have a problem with mobility. So it's cool. So that's why I wanted to be a software engineer. And first I have a question. How many people using Google Navigation or Apple Navigation? Thank you very much. Everyone using. So here's your practice. On the left is Apple Navigation, and which is from Roppongi to Nihonbashi. On the right side is Google Navigation from Shibuya to Chrysalis. And today, this talk is for who are new to algorithm and interested in the route navigation. And I explain this algorithm in the JavaScript. So if you are familiar with JavaScript, it's also good. But don't worry, most of my presentation uses a diagram, so you don't have to know the JavaScript. So this is the agenda. I have 3 things. And one thing is, before we dive into the algorithm things, a few things should know. So and after that, I explain the algorithm with diagram. And after that, let's implement in JavaScript. So some kind of definition. What is the pathfinding algorithm? Pathfinding or passing from Wikipedia, it's too long, didn't need. So find the shortest route between 2 points. It's a pathfinding algorithm. And there are a bunch of algorithms in the world. So, and I'm going to talk about Dijkstra's algorithm because it's very basic algorithm and good for understand for beginners. And let me ask, how many people know Dijkstra's algorithm? Oh my gosh. Well, so many people know. So if there's an expert, correct me if I'm wrong. And first, Dijkstra's algorithm, of course, designed by the Dijkstra, Edgar Dijkstra, who is a Netherlands computer scientist. And he designed the algorithm in 1959. And the Dijkstra algorithm is one of the most famous shortest path find algorithm. And this algorithm uses a directed and weighted graph. So first, I want to explain what is a graph. So a graph is one of the data structure, which is a non-linear data structure and consists of vertices or nodes and edges, and which connect a pair of nodes. Here's nodes and edges. And here it's a real example. Graph structure is uses for many famous companies. So on the left is a diagram visualization of Facebook connection, and it uses for graphs. And the right up one is LinkedIn connection diagram, and right down is some handwriting diagram is a Twitter connection. And I explained the graph has vertices and edges, and also in the Dijkstra algorithm we use another parameter. One is directed, and graph can have directed or undirected. And for example, let's think about the Facebook communication. If I send you a friend's request, and when you apply, the connection is two direction. I'm your friend, you are my friend. But if it's a Twitter, I follow something, but this is one direction. I follow, but maybe he doesn't follow or something. So this is directed and undirected. And Dijkstra algorithm uses a directed graph. And one more thing is weight. Weight is some kind of edges parameter. It's similar to distance or time or something. And before talk about algorithm, every algorithm solves some kind of program. So we should know what is a program Dijkstra algorithm solve. So this is of course a shortest path program, finding a path between two vertices in graph, and sum of the weights of its consist edges is minimized. In the real case, the nodes corresponds to the intersections, and the edges correspond to road segments. And each weighted by the distance of its road segment. Here is Google Map navigation. Okay, so let's talk about how it works. And Dijkstra algorithms are basic 4 steps. Step 1, find the shortest node. The step 2, update the distance of the immediate neighbors of this node. And step 3, repeat steps 1 and 2 until you've done this for every node. And return the shortest distance to reach the goal and optimal path to do so. And let's think in time. I give you 5 minutes and a piece of paper. So let's think what's the shortest distance and what is the shortest optimal path. you need a pen, stuff. Yes, that. You mean the pen?
So you took it out in my brain.
Here's some hints. Maybe we can use 3 types of memo. One is the distance, one is the keep track of the shortest distance to each node, and one is the path, keep track of the node before each node. And visited is the keep track which node has been visited. In the algorithm, maybe we can use 3 other data structure, other data store. Finish? If you finish, sorry, let's talk neighbors.
So I have to have these in.
What's the
Yeah.
What's each year? It's a good question. How does the algorithm
Okay, time is up. Okay. Okay, let me ask. Does anybody know the answer the distance and the optimal path? Okay. Somebody ready? Oh,
Have a guess.
okay.
So I went from start
Yeah.
to C to D to F and then to goal.
And shortest distance is how much?
Distance is 9.
9. Okay. Everybody same answer? Oh, please. Yes.
Same answer.
Same answer? Okay. Maybe everybody gets. Oh.
The other option. So start E, F, goal.
Yes.
Also
Yeah.
9.
Yeah.
Those.
Same.
Yeah.
So let's make things easier. I said avatar is also hero. I want to go to CC. And first, I'm here and home. And I find 3 connections, which is to B and C and E. And I write to my memo and each knows and distance, which is B equals 3 and C equals 2 and E equals 3. And I wonder what is the shortest node before next I move. And I move to C. And I find the 2 connections which are to D and E. And to D, there are no nodes in my memo, so I write D and also write distance, which is 3. And I found another connection to E, but I already know the E, and the shortest distance to E is 3. So if I go to E from home to C to E, it takes 7. So I don't want to override my memo to E. And next, I have 3 hasn't been visited nodes, which are B and E and D. So I move next B. I found the 2 connections, and I write in my memo new node Z, and distance equal 11. And also, B has a connection to C, but I already know shortest distance to C is 2, so I don't overwrite my memo. And next, I move to E. I find 2 connection, and both nodes is a 2 new connection, and I like in my memo F and I, and also distance 6 and 10. And let me ask, which node should I move next? Anyone? Anyone?
Well, D looks like the shortest of the unmuted nodes.
Yeah, correct. I move next to D because D is the shortest node. And I have I found 3 connections to Z and CC and F. And so I like my memo and override the Z equals 6 because if I move to home to C to D to Z, it takes 6. So I override my memo and I found CC. This is a new node, and I write in the memo CC and 10. And next, I move to F, and I found 2 connections. One connection to CC and C, and I override CC equals 9. And I found CC, but this algorithm checks every node. So if the algorithm won't stop here, I check I and Z. And finally, I found the shortest path and shortest distance and shortest path. This is explain algorithms with diagram. So, any questions so far? I think.
So you determine the priority by the distance instead of the level of nodes, is it?
Yes. Yes. Priority of distance. Yes. So this is. I think it's original algorithm. So it considered only distance. Okay, let's move next. So let's implement in JavaScript. So final result looks like this object. The distance is 9 and passes home and to E to F and CC. And first, I set the variable which hold the tracks of the shortest distance. At the beginning, the distances should look like this. I have B, C, E, and set goal CC. And in the beginning, I set CC to infinity. For instance, at that moment, I already visit B, C, E, D, Z. So at the moment, this object looks like this. I out D3 and G11. And next, I declare the variable which keep track of the passes. Passes is right before each node. So at this moment, passes should look like this. I keep track the one node right before this node, each node. And also, I set the array which keep track which node has already been visited. And I make a helper function. This function it takes distances and has been visited array, and return the shortest node, which is a node I should move next node. And finally, here's a Dijkstra's algorithm. Dijkstra's algorithm is a little bit long, so I separate the 3 sections. And then part 1 is set variables and set the passes initial value. And next, here's the main part. It takes a node and find the connection of each node. And if the distance, find new distance is short, I override memo. If not shortest, I do a debug. And here is a graph structure, which is the same as your hand paper. And this is a helper function which find the shortest node I should move next. And here is Dijkstra's algorithm. I start debug. Oh, sorry, I use VS Code and the right side is real code, and the left side is a debug console. And I already set the variables, which is I set as a memo, which is a distance and passes and has been visited. And also which is a node and connection, which is an n. So first, my debug stop here. Now I take a C, it's the first node, and check D, which is next node. And I keep the memo, which is E. And next check, I move to B. And check the every node, B, and next G. So G isn't in my memo, so I write G in here. And also G is from B, so I write in the path, which is G. And I write has been visited, CBE, and Z here. And next is now I am F. I check CC and CC. And finally, there are no nodes I didn't visit it. And this while loop ends. Oh, sorry, I missed. After through the this while loop, I'm going to here, and in this while loop, I set the final result, which is before final result, I set the optimal path, which is from passes, and set the node, which is here, home, E, F, CC and return result. And that's it. Thank you.
There we go.
All right, it worked out. All right, big round of applause for Darren.
See if this works here. All right, it works. Okay. Hi everyone. My name is Darren. So I was going to prepare for this presentation, but then I read that Elon Musk spends like no time preparing for his talk, so I figured that would be a good idea. I was just told about this a couple days ago, so if this is kind of awkward and random, I apologize in advance. Like, we can make this interactive too. So where are we live streaming from? Is this coming from here? Okay. So is anywhere in this area good? Like, can I walk around and stuff?
It's quite angle.
Okay.
Yeah, for the most part.
Okay. All right. So let me just give a quick introduction. My name is Darren. I moved to Japan like 2 months ago to join Mercari, and don't understand anything about this country yet, but it's fun. It's very interesting. I'm a principal engineer at Mercari on the data team. And before joining Mercari, I used to work at Google for a while on the Gmail team. And then kind of jumped around a bit from there. I did a mobile game company, moved from games to AI deep learning research, went from there to quantitative trading, and then from quant trading to Mercari. And I'm currently working on, I guess what you could call big data type stuff. So I've worked in a lot of different areas in tech. What I want to talk about today is what I call full stack thinking in a cloud computing world. What I was actually going to title this presentation was what you can't learn at coding bootcamp that's really important. But Mike told me I shouldn't title it that. So I changed it to full stack thinking in a cloud computing world. And I noticed that like you have a full stack curriculum here for the students here. So it's good that Code Chrysalis is thinking about full stack stuff. So without further ado, let's see if my clicker works. Oh, figured it out. Okay. So I wanted to start with a little story. I started working on the Gmail team in around 2005, and the first project that my tech lead gave me was this little bug that we had to fix, and it was a stuck on loading bug. So this GIF, however you want to pronounce it, it kind of that's a really big controversy. So this GIF it kind of shows what was happening. Basically, like the old version of Gmail, so there would be a progress bar that would be loading, and then it would just get like sort of close to the end and just stop. And we didn't know why. And we got reports of this bug, and they kept coming in. So my tech lead said, your first project on Gmail, and I worked on the Gmail front-end team. And the front-end team, I mean so the browser side, so it's a big JavaScript application, and then the server side, which was a big Java server that the JavaScript app connected to. So we call that the front end. So let me throw this out to the audience. Are there, what would you guess could cause this problem, this stuck on loading problem? Any guesses?
Authentication error.
Auth error, good guess. Okay. And any other guesses? And this is like 2005, so it doesn't make a big difference. Like these sort of bugs keep coming. Like I Googled Gmail stuck on loading when I was making this presentation, and I still see them. So didn't quite get it. Okay, so auth errors. Any other guesses? Okay, so I'll tell you what happened with this bug investigation. So as I said, Gmail is a very big JavaScript application. And if you think about what happens when you load Gmail, basically you go to mail.google.com and the server sends back this big blob of JavaScript, and it goes to your browser, and your browser loads it and processes it, and it renders the web app, and then you can go on. So something in this process was broken, and we had no idea what. So the first thing we had to do was figure out how to replicate this. And if you can't replicate a problem, it's really hard to fix. So we would get reports of this, but when we would go to look at the server with the issue, it was gone. Like the problem disappeared. So we were kind of like chasing this bug. We were chasing this error, and I don't remember exactly all the changes we made, but we put this bit of code into the JavaScript loading part. So it would load the first piece, and then the first piece would wait for the second piece, and if it didn't come within a certain amount of time, then it would ping the server, basically sending this error. And then we connected that to this monitoring system, and the monitoring system to me. So so then people would get stuck on loading, and it would ping this monitoring system, that system would ping me, and I would be like, oh, there's a stuck on loading server, I gotta go find it. So finally one day, this error came in, and we still didn't know. It had been like weeks, and we're trying to figure out what was stuck on loading. Is it corrupt JavaScript? Is it something with browser extensions? Browser extensions was the leading contender. Like back in 2005, everyone had these awful browser extensions like Yahoo, Search Toolbar. There was a Google toolbar also. We killed that project. But everyone had these awful browser extensions, and they messed with the JavaScript. So that was our leading contender. So we got this server that was throwing these errors, and I went and looked at the server, and I found the actual JavaScript that was served to that user who was hitting those errors right then before it switched servers and the error was gone. And I pulled up the JavaScript in a binary reader. So like binary readers are applications to look at the actual binary code of a file. So typically you don't really look at them, but when I pulled it up in a text editor, it started out okay, and then it was just garbled. So I look in this binary file reader, and it's normal JavaScript, and then zeros. And I was like, how are there zeros? So it's like JavaScript code, and then it's just filled with zeros. So are there any guesses for how the zeros could end up in JavaScript? Okay, so what happened was the hard drive had become corrupted. So the hard drive on the server got corrupted, but not corrupted enough that the server would crash, just corrupted enough that the JavaScript that we were serving got corrupted, but the end of the JavaScript. So we were sending like partially good JavaScript to the client, and then sure enough, it would start loading, and then it would die because it couldn't finish loading because it's all zeros. so after weeks of looking for this, we found out that like hard drives were getting corrupt, and corrupt hard drives were killing Gmail loading. And it was so far down the stack, and the fix for this actually was there was like so basically FS check, FSOC, like however you want to pronounce it. It's a Linux command that does a file system consistency check. Basically, FSOC was failing, which meant that it knew the hard drive was corrupt, but the machine was not taken out of service. So later on, when the server would start accumulating more errors, it would automatically be taken out of service, and that's why we saw this thing where it would switch servers and then it was fine. So we ended up making a change for, at the time, like hundreds of thousands of servers, so that if FSOC failed, that machine was instantly taken out of service. And this is so far from what I was supposed to be doing in my job, right? Like, I was supposed to be working on this JavaScript application, and the fix for this problem was actually an FSOC error. Like, literally on the bare metal, this is like, this was kind of before cloud computing. You didn't have access to like virtual servers so easily. And that was the fix. So we flipped that one bit, and all of a sudden these stuck on loading problems disappeared. So that's kind of like a really good example from my own software engineering history of why this kind of full stack thinking is really important. So why this was actually a problem, has anyone heard the term NTBF? It's a mean time between failure, and hard drives have the statistic of how long they're supposed to last. And they're supposed to last, the rating is like between 10 and 100 years, but that's only if you run them part-time. And Google and now like Amazon, they run hard drives 24/7, and they're cheap commodity hard drives, and they fail all the time. But even given 10 years, well, we have like 10,000 servers. So if you have, so 10 years is, let me see, 87,000 hours. If you have 10,000 servers, that means that every 9 hours, on average, a hard drive is going to crap out. And that means that like every day we're seeing these problems of these server errors coming up. So this is very far down the stack, but it's completely affecting the user experience. Second story. I moved to Korea in 2010, and before I moved, I had all these desktops, like from college basically, that I wanted to get rid of. But before I got rid of them, I booted it up, and I just wanted to see what was still on them. So my college desktop, it was running Windows XP and Kodos and Visual Studio.net, like the 2002 version of Visual Studio, I guess. And my expectation was, oh, like hardware's gotten so much better in the 10 years since then. Like this is going to be really slow. But in reality, I booted up the computer and went into Visual Studio. It was so fast. It was like super slick and so fast. And it was really weird because we always think that, you know, software is getting faster, hardware is getting better, everything's getting faster. But actually maybe not so much. Actually, it seems that we as software engineers, programmers, we're beating the hardware in a bad way. Like the hardware is getting better, but we keep writing more, bigger and bigger software, and our software keeps getting slower. So why I wanted to talk about this is that, you know, as you're building apps, as you're building web apps, mobile apps, whatever, you kind of have to take this into mind that we're creating more and more complicated frameworks. Much of this course, Code Chrysalis, is focused on just kind of dealing with all these frameworks and how do you put stuff together. But yeah, the actual hardware is going to make a difference. So question time again. How much faster are processors in 2018 now compared to 2005? Any guesses? Yes?
20%?
20%, okay. Alright, you ruined it. Yeah, so processors have not gotten faster. So the fastest processor in 2005, it was around like 3.8 gigahertz. Yeah. So most people think it's 100 times faster, 1,000 times faster. The fastest processor in 2018 is like 5 gigahertz. It's kind of lame. Most people don't think about this, like processors stop getting faster. And this is the clock speed of processors. So does anyone know why they stop getting faster? And we could go higher, like it goes up to like 8 or 9 gigahertz, but they have to be cooled by liquid nitrogen. So any guesses why processors stop getting faster?
Heat generation?
Yeah, heat. Yeah, heat and power basically. So we're cramming more and more transistors onto CPUs, and but the clock cycle, that's basically, and pardon me if I butcher this, I'm not an electrical engineer. So basically the clock cycle is an oscillator creates a sine wave which gets turned into a square wave, and 5 gigahertz means 5 billion times per second this cycle is going, and that's turning transistors on and off 5 billion times a second, and it generates heat. And we can increase the speed a little bit, but as you increase the speed, the power consumption goes up by a cubic factor. So like the frequency is related to the voltage. If you double the voltage, the power goes up by a factor of 8. So we reach like physical limits in how fast processors can go. So what have we done? Oh yeah, like this was my comment before about we're beating hardware as software engineers. So the solution to this, of course, is we start parallelizing. So processors, they can't get any faster, but we can put multiple processors on a chip. So let's see. So this on the left, this is like an old Pentium chip. And you see lots of little chips here, but it's just one core. And then this on the right, this is one of the AMD Threadrippers. Like pretty cool name, first of all. But this one, each of these little chips is its own core. So this is like a 20-core processor or something. But with parallelization, we get complexity. So processors get parallelized, pull data, and it goes back to the server, and then it goes back to the client. It's very, very simple. It's just this nice self-contained little like request-response pattern. And then sometimes when you've got bigger, the database might be on a different server. It's probably good to put it on a different server anyway. But it's simple. It's very easy to understand. But now we have applications that run on dozens of servers, hundreds of servers, thousands of servers. And we complicated things. So this is Kubernetes. Earlier when I was talking about the Gmail stuck on loading problem and how we changed configuration on the bare metal, and there was this kind of self-monitoring thing that would restart services. That's Kubernetes, basically. It was an internal system called Borg. That name got leaked, so that's public now. And then that became Kubernetes. And Kubernetes is this crazy system that comes out of Google where you split services up into these little things called pods. and a pod is like a self-contained microservice. And the pods talk to each other over the network, and then you combine the pods into these nodes, and then the nodes talk to each other over the network, and there's this master scheduler, and like the point is, web apps have gotten incredibly complicated. So as a modern developer, it's incredibly complicated just to figure out what the request flow is, because it's not just browser sends a request, and server, database, server, browser. It's like browser sends a request, and it goes to some service, which is load balanced by this master service. And that gets sent to some other service, and that gets sent to some other service. And just keeping track of the request flow has gotten very, very complicated. But it's actually more important now than it was then for tracing problems and tracing performance of applications. Let's see. So my talk is about full stack, and what is the full stack? Well, we saw it briefly before in the curriculum. I have it here actually. Week 3 through 6, full stack and solo MVPs. Sorry, this is a free ad. We bring you full stack starting from the back end and moving to the front end. You will work on a slew of solo and team projects, ending with a full stack project that you get to choose and build from scratch. Topics we cover include GraphQL, Node, Express, React, Redux, continuous integration, delivery, team workflows. Yes, so that's like a kind of a modern full stack. There are other ways to think of the stack. You could think of it in terms of network layers. This is common in college networking classes. At the bottom, it's like bits on a line. So it's like voltages on a line. Is it a 0 or a 1? And then Ethernet frames and packets, and it goes all the way up to the application layer. This is useful for a network perspective, but from a programming perspective, maybe not so useful. So we could think about the LAMP tech stack. This was the full stack 10 years ago, and this is actually very similar to the simple web application stack that I was showing before. You can see this is 10 years ago because the browser is Firefox. So it's called LAMP it's because it's Linux, Apache, MySQL, PHP. This tech stack is actually still used. I mean, there's nothing wrong with it. It was very simple to understand. This line splits client side and server side, and then on your server, you would run these services. You'd run your web server, and then that's basically running PHP. You code your web app in PHP and sends database requests to MySQL and goes up the stack and out. But things are getting complicated. So this is from a blog post from CircleCI, and CircleCI is a continuous integration project. So basically, like as you check in code, it's constantly building it and stuff. And I love this post. This was from a couple years ago. I highly recommend you read it. I'm just going to read this little blurb here about how web apps have gotten complicated. So all I need to do, I need to split my simple CRUD app, and CRUD is create, read, update, delete. It's basically like the simple web request cycle. So all I need to do is split my simple CRUD app into 12 microservices, each with their own APIs, which call each other's APIs, but handle failure resiliently, put them into Docker containers, launch a fleet of 8 machines, which are Docker hosts running CoreOS, orchestrate them using a small Kubernetes cluster running at setp, figure out the open questions of networking and storage, and then I continuously deliver multiple redundant copies of each microservice to my fleet. Is that it? Okay. Just to go back a step, all we want to do is this, right? All we want to do is serve a simple web request from a database, but the modern implementation of this has gotten incredibly complicated. And the only way to understand this is to have insight into the full stack and what's happening to the request as it goes up and down the full stack. So web apps are complicated. Front-end frameworks are also complicated. Like a big part of any coding camp is going to be front-end frameworks. This is like a satirical post based on the last blog post from the previous slide. So this was just this little blurb, and this is from 2 years ago. It says, another library? Well, what's Babel? Oh, Babel is a transpiler that allows you to target specific versions of JavaScript while you code in any version of JavaScript. You don't have to include Babel to use Rxjs, but unless you do, you're stuck with using ES5. But let's be real, it's 2016, you should be coding in ES 2016 plus, like the rest of the cool kids do. ES5? ES 2016 plus? I'm getting lost over here. So these are actually, they're like versions of JavaScript, and React is a front-end framework, and a transpiler is something that it takes code, it basically like translates code from one language to another. All we want to do is like write web apps, and this is kind of the state that we've gotten in. And this is 2 years ago, so some of these things are actually old. I actually got stuck in front-end framework hell for a personal project I was doing a couple years ago, because when I was at Google, like we had all these internal frameworks and libraries and stuff, and then you leave and you realize that the world is chaos. Like all the amazing stuff that you had that like 10,000 engineers had built, it doesn't really exist in the real world. And people love building front-end frameworks. So there are like an endless number of front-end frameworks, an endless number of like modular JavaScript frameworks and web frameworks like Angular, React, Vue. I mean, they're endless ones, and they keep coming out. And you can actually spend all your time just trying to pick a front-end framework and not actually building anything. Like, if I could give you any advice about front-end frameworks, just pick any, and then just move on. Like, they're all pretty simple. What else is getting complicated? Big data is getting complicated. So big data, it's changed a lot in the last 10 years also, but what exactly does Hadoop or Amazon Elastic MapReduce, like what exactly does it do? Similar to the previous blog posts, which are kind of parodying how complicated front-end frameworks and web app development have gotten, there was this blog post I read like a couple years ago, and some guy he was talking about running this MapReduce, and basically what it had to do. Is anybody familiar with MapReduce here? Like, raise your hand if you're familiar with MapReduce. Okay, so what MapReduce is basically it's a way of processing massive amounts of data, and it comes out of Google also, and then they wrote this paper, and the Hadoop project made an open source version. So basically what it does is it takes a huge amount of data and it splits it up into manageable chunks, and it sends each of those chunks to a different processor. Something happens, and then it recombines them. Reduce means combine, basically. It recombines them, and then it sends the result back. And it's the only way that you can work with these huge data sets, like petabyte level data sets. So I read this blog post. This guy was talking about how he was processing like chess game results, and he was processing them on Hadoop by running this MapReduce, and it took like 45 minutes or something, and like 100 machines. So this guy writing the blog post, he's like, that's weird because there's really not that much data. It's like a gigabyte of data. And like a gigabyte is a tiny amount of data. Like your phone has multiple times that amount of storage space. So what he did was this. He just turned the whole MapReduce into a sequence of Linux pipes. And these programs are from like literally the 1970s. So what this is doing, it basically like, I left out the actual code here, but find looks for files of a certain type, and then it pipes it into this thing called mop, which is just looking for a text match basically, and then this was piped into this other mop, which was taking the results of the first one and putting them together, and he ran it like there you go, 235 times faster. So 230, like that's crazy. So the first one, it took 45 minutes and probably cost like $20 of compute time or something. And then the second one, just running a few simple command line programs from the 70s, he's doing big data. So big data has gotten complicated. Everything's kind of gotten complicated. What's the point of all this? So the point of all this is first principles. And I started off this talk by mentioning Elon Musk. I love Elon Musk. He's a super cool engineer. He talks about first principles a lot. So first principles, this was the coolest thing that I saw this year. This was the Falcon Heavy launch. He launched a Tesla into space. It was just the craziest thing. It was the coolest thing I saw all year. And Elon loves talking about first principles, but he's talking about first principles for rockets. So first principles means if you look at a problem, rather than looking at the problem in relation to similar problems, you have to get down to the heart of the matter. For rockets, the first principles that he found were, well, how much does it cost, how much does fuel cost, and how much do the raw materials for this rocket cost? Well, it turns out that fuel plus raw materials was like something really low, like 2% of the actual cost of the rockets. So he just decided to start a rocket company because he thought he could make it cheaper. There's a big gap between the cost of rockets and the cost of the materials, which means that there's a business opportunity there. So similarly, this is talking about physics and the speed of the processors that I was talking about earlier. The first principle there is this physical limit of how fast we can switch this thing on and off. But software engineering also has first principles. Just as physical limitations are first principles for a clock cycle upper speed and rockets, code decisions very, very low down the stack can affect hugely the application level. This is something I think about all the time. In my current job, I'm managing the data pipeline. So what that means is we produce a lot of data when people use our app. And then we consume data on the other side for stuff like machine learning and business analytics. And that data flows through the entire pipeline. It's coming from phones, it's going into databases, it's in logs, and then from there we have to get it all together and put it into some useful format for processing. So if you just focus on frameworks and the connecting libraries, you'll miss the bigger picture. And this is like the best advice I give anyone going into engineering nowadays is that it's very easy to get lost in the frameworks, like I was talking about earlier. There's just so many of them, and you can spend all day trying to choose the best one and actually just trying to connect them. But connecting frameworks is not the important thing. We're trying to build things. So this is actually the difference, I think, between being a programmer and an engineer. Programmers can be very successful just pulling frameworks together, but you're necessarily only looking at a small part of the problem. But software engineering is kind of looking at the bigger picture. It's working with the frameworks, and rather than letting the frameworks wrangle you, it's you wrangling the frameworks. And sometimes this involves going down to the bare metal on the machine and seeing why there's zeros in your JavaScript. Sometimes this involves going all the way to the top level of, well, what is the JavaScript sending to the what is the JavaScript sending to the web server? If it's not sending the right data, then we can't possibly be doing the right data analytics. So this is the full stack nowadays. It's gotten more complicated, but it's also gotten much more interesting. And with that, yeah, that's it. Thank you very much. I'd like to open up for questions. You can ask questions about anything, just past work, future work, whatever. Space. Any questions?
Questions?
No questions.
Yeah.
Yes.
If you do full stack, right?
Yes.
How do you know what you should be responsible for?
That's a really good question. So one of the problems with doing full stack is kind of what you're bringing up here. So you can't be an expert in everything, right? It's impossible to be an expert in everything. And a lot of people will claim to be full stack, but like they're not really. So when I talk about full stack, I don't mean that you should like be an expert in every different layer of the stack, but you should understand what's going on in every layer of the stack. And most jobs in the real world are actually not full stack. Like it's kind of rare for. Actually, let me walk that back. So the smaller the company, the more likely you'll be doing full stack. The bigger the company, the less likely you'll be doing full stack. So at a small company, if you're doing full stack, I mean, what tends to happen is people tend to gravitate either towards back end or front end because most people like one or the other better, and that's fine. But some of the best back end engineers that I've met were happy to go into the JavaScript side every now and then. And some of the best JavaScript engineers that I met were happy to go into the server side every now and then because their JavaScript is sending requests to the server. I'm not sure if that answers your question.
Thank you.
Sure. Yeah.
So you made the comparison with like processes are only getting so much better these days, and you expected your Visual Studio Code to be like really, really crappy, like 2005 machine.
Yeah.
Should we like look towards like how engineering was done back then to write code now, or should we just all run Visual Studio Code 2005?
I think there are a lot of lessons to be learned from coding back then, but at the same time, our modern tools are so much better. Like Visual Studio is a fantastic piece of software, actually, and many people from Silicon Valley, they just like crap on everything Microsoft just because, but Visual Studio, it's actually really good software. C# it's a really good language. So we have these modern tools, but the problem is it's so easy to spin up resources these days that I see this problem all the time, and I help startups with stuff like this sometimes. But as a startup, you have this product, and you raise money, and you start getting more users for your product. And the easiest thing to do to support more users is to just copy your application server multiple times. So you just spin up like 10 instances or 20 instances. And I see this all the time. It's totally ridiculous. Like, it's really easy to press a button and spin up 100 instances of your app, but your app is only serving like 2 requests per second, which can run off of a modern Android phone. So the reason like it's become so easy to work with cloud computing, and this is great for Google and Amazon, that it's easy to spin up resources. But we lose sight of how efficiently you can actually do something. And when you were coding 15 or 20 years ago, you were resource constrained. You couldn't very easily spin up multiple servers. So like a really good example for this, I was working on, and imagine taking that and then putting it into the cloud and then spinning up 100 instances of that. Well, now you have a really high performance service. So I'd say like pretending that you're resource constrained is a really great forcing function for writing better code. But sometimes like you just want to move fast because for business reasons you have to move fast. And it's easier to just kind of spin up instances. But yeah, I definitely recommend thinking in a resource constrained way, because it'll force your application to be better. Any other questions?
Actually, I have a question
Sure.
with your status quo just right now, because in my sense, I think logic should stay as its best way instead of the resource constraint, because the hardware will getting improved from time to time. So what is your balance between like, okay, writing fastest code could like getting some redundant code from refrain from running, but somehow that would crack the logic if you get one.
Yeah, so I think so there are certain instances where you can wait for hardware to catch up, and like we did this project on Gmail like quite a while ago where we rewrote the entire front end, and we rewrote it in a nice object-oriented manner. But the problem was that like old web browsers couldn't support the it couldn't support like the function call stack basically. So it was so nicely decomposed and object oriented that very deep you get like function calls that were going dozens of levels, and there was a memory leak in IE6, and it just didn't support it. Like we were maxing out the capabilities of those browsers. So we actually made a decision that sooner or later IE6 was going to die, and we were just going to stop supporting it. And Chrome was getting better and better. The JavaScript engines, so the first Chrome came out, it was super fast, and then all the JavaScript engines, Opera, Firefox, IE, they all got super fast. So in that instance, technology caught up with us. All the browsers got better, and it caught up with our coding practices. On the other hand, I think very often, from a business perspective, like from the business side, you'll find yourself in a situation where you have to write better code, and it's very easy for engineers to spend money. It's very easy to write bad code that runs on like hundreds of servers, but if you find yourself in a position where you're not serving a lot of requests, but you're already running on many servers, and you want to grow your business 10x or 100x, you can plot out how much it's going to cost per year. And if it's like, okay, well, we're already spending $10 million a year, and it's going to cost $1 billion a year to run this service, if our users go up 100x, then at that point you have to go back and write better code. So it's definitely a balance. With games are like a pretty good example of this also. So game developers are some of the best developers in the world, and they're always pushing the limits of hardware. Literally every time a new GPU comes out, as soon as it comes out, the next day, somebody has maxed out the capabilities of that GPU. It's super easy to do. So they're like pushing the hardware as hard as possible. And then on the other side, on like the inefficient cloud computing side, we're just overusing resources as much as possible. So there's somewhere in the middle that is like an ideal place.
Saw my talk on Rxjs 2 weeks ago. So 1, 2, 3, 4, 5. All right. So this is basically an extended version of that talk. So I do have some new material, as well as a couple more examples. But if you start feeling deja vu at some point, it's completely normal. So don't worry about it. A little bit about myself. I've been doing engineering for about 6 years now. I focus primarily on JavaScript, Rxjs, and Angular, and I like writing about these things a lot on Medium. So I actually have a 4-part blog post that goes over implementing observables from scratch. So if there's any details tonight that you missed out on, go ahead and check that out. So tonight, I'm also a contributing author for the Angular in Depth publication on Medium. Do we have any Angular devs in here? 2, okay. Have you guys heard of this? All right, so what this is if you have any interest in learning about how a framework like Angular works internally, like how change detection or dependency injection is implemented, there's a bunch of great articles on this site. So tonight I'm going to be talking about solving difficult async problems, primarily the kinds of problems that come up when you're building reactive user interfaces. We're going to see that we're going to do that simply by changing the way that we think about events. When you work with observables, you're really focusing on events and other asynchronous data as well. In order to do that, we're going to use a library called Rxjs. Now, who here has heard of Rxjs? Okay. How many people have worked with it? How many people are experts in it? Okay, good. I can get away with some stuff tonight then. So basically, JavaScript does not currently have support for observables. They're just a data type. There's a proposal to add them to the language. So we should be getting them within the next couple of years, but until we get them natively, you have to use a library, and Rxjs is the most popular library for working with observables. It's actually what Angular uses internally. It's very easy. You just use your package manager of choice, in this case npm. Can people see that okay? Okay, you just use npm. You import whatever you need from it, and then you're good to go. There's currently 2 versions of the library. There's version 5 and version 6 that are currently supported. Conceptually, they're exactly the same thing. It's just there's some slight syntactic differences. I'm going to be using the version 5 syntax tonight, but it's really not that big of a difference. So what kind of things can we build with this? Well, we can build sites like this. We can build these very reactive interactive sites. So you notice with Apple's site, as soon as you start typing into the search box, you're immediately getting a filtered list of results based on what you typed. It's like an autocomplete feature. And with Netflix, simply hovering over one of the images causes a request to be made out to one of their servers. They'll pull down a video and start playing a preview of that show for you, just by hovering over one of the images. So sites these days tend to be very interactive in real time. But as engineers, we can't really build it using like the stuff JavaScript gave us back in the 90s for working with events. We need something a little more powerful than add and remove event listener. So we want something like Rxjs. But as the previous speaker mentioned, there's a lot of libraries and frameworks these days. So you might be wondering, why learn yet another one? Why can't you use the existing async stuff like callbacks or promises when you're building reactive UIs? So let's briefly go over why those might not be up to the task. Real quick, callbacks. Callbacks make async programming difficult. Your code starts to look like this. a lot of times you have to have shared mutable state to manage concurrency and prevent race conditions, and then everything catches fire and everyone dies. Not the best approach. But what about promises? We got promises natively in JavaScript a couple of years ago with ES6, I believe. Promises are great, but they only represent a single future value. So they're great for representing something like an XHR request to a web API. But a lot of times when you're building these user interfaces, you want to be able to represent multiple future values. So maybe you want to represent a stream of dominance, or multiple XHR requests if you're consuming paginated data, or animations. So the point is you want to be able to work with multiple future values. Another limitation of promises in this context is that they're not cancelable. And while they can be useful in certain scenarios, a lot of times when you're building a reactive UI, you want to be able to start something like an animation or an XHR request, and then later on you want to be able to cancel it based on some information you've received from the user. So if you look back to that Netflix example, if a user hovers over one of the titles, and then we issue that request to load that video, and then they change their mind and go hover over a different title, we'd like to be able to cancel that animation and that request if possible. Netflix definitely doesn't want stale data showing up when somebody hovers over a different title. So if callbacks and promises don't work, what can we use? We can use streams. Tonight I'm going to use the terms stream and observable pretty much interchangeably, because that's how Rxjs treats them. So streams are just some series of values produced over time. And there's two benefits to doing this. Number one is it lets us treat events in asynchronous data as collections. So much like an array is a container for synchronous data, for stuff that you already have in memory, an observable is just going to be a container for asynchronous data, for stuff that arrives over time. And the benefit to doing this is that we can now use operators on these collections of asynchronous data to compose new collections. And we'll see a lot of examples of that tonight. But much like arrays have map and filter for producing new arrays, we're going to see that observables have those operators plus many more. So a good way to visualize this stuff is using what's called a marble diagram. And if you dig into the Rxjs documentation, you'll see these everywhere. I'm going to be using them in all of the examples tonight, so I want to explain briefly how you read them, because the first time you see it, it's kind of like, what the heck is going on? So the arrows here, this represents an observable or just some stream. The shapes inside of it just represent some asynchronous data. Could be dominance, and those are arriving over time. The box that says filter is an example of an operator. And what operators are in Rxjs is they're basically functions. And they take in one or more streams as an input and immediately produce a new output stream. This is very important, is that they don't actually mutate their input streams, they always produce a new output stream. So one of the rules of Rxjs. And in this case, we're simply creating a filter, so anytime data comes in on our input stream, we filter it, in this case, producing a stream that contains only circles. Again, a little bit abstract and hand-wavy, so let's see a more concrete example. If we take the same setup and simply reskin it, we can build something that'll let us take in a stream of tweets and filter it in real time based on username. And we'll see some code for this in just a second, but conceptually what that would look like is we have, we're hitting Twitter's API, let's say, we're getting a list of tweets, and we're just filtering them based on the username Alice. So how we would set that up is, we have our input stream, we have our single operator, and we have our output stream. And then as tweets come in, we're just checking to see if they came from Alice. If so, we re-emit them on our output. Otherwise, we do nothing with them. Okay. And this, the structure of this is something we're going to see over and over again in the examples tonight. So I just want to point out that the first rule of Rxjs is that everything can be modeled as an observable or as a stream. And so we see here that our inputs to our problem is just some stream of tweets. But notice that our solution is also represented by a stream. In this case, it's a stream of all the tweets that came from the user Alice. So whenever you go to solve a problem using Rxjs or using observables, the first question you usually want to ask yourself is, what does the solution to my problem look like? And how can I represent that as some stream of data? Then you identify what your inputs to your problem are, In this case, it's a stream of tweets from a bunch of different users. And then it really just becomes a task of figuring out which operations you need to perform to produce your output stream from your inputs. The code to solve this problem is actually quite simple. So here we have get tweets observable, which is just some wrapper that's making requests to Twitter's API and producing this tweets observable. Then on line 2, if I had line numbers, we're calling the filter operator, saying we only want tweets from Alice, and then last but not least, we subscribe to it. Notice how similar this looks to an array-based implementation. So if we weren't dealing with asynchronous data, if instead we had all of our data in memory at once in an array, it's a pretty similar setup. We just have an array of tweets, and then we call filter on it. In this case, using the filter method off of array's prototype. So one thing we're going to see over and over again tonight is that if you're comfortable with arrays, a lot of the intuition that you have for working with arrays can be directly transferred over to working with Rxjs. Yeah?
Good question. The dollar sign on the right side, does this mean it's observable?
I've seen the convention before, but you don't have to use that.
Okay.
Yeah, just
Yes.
for sure. Okay. So with that out of the way, let's look at a real-world example here of creating a drag event stream using Rxjs. Now, I covered this example a couple of weeks back, but I want to go into a little more detail this time. So, what is a drag event in the browser? Well, it lets us build things like this, right? It's where you click on some DOM element and drag it around the screen. Now, ignore for a second that you can actually subscribe directly to drag events, drag start, drag end, as well as drag. Let's take this as a learning opportunity and see how we could take something like a drag event and build it using simpler events that we get from the browser. So when you look at this animation, you can see a drag event is really 3 things. It's a mouse down event, followed by some number of mouse move events, and then eventually it's terminated by a mouse up event. So if we wanted to solve this problem using the same approach that we used for Twitter feed, we would say our inputs to our problem are a mouse down stream, a mouse move stream, and a mouse up stream. And our solution is we want a stream of drag events. So using marble diagrams, the way we would model this is as such. We're going to have 4 streams, our 3 inputs, mouse down, mouse move, mouse up, and then our output stream, which is going to be drags. This is how you can create a stream of DOM events using Rxjs. So we're using from event, which takes in a reference to a DOM element and a event to listen for. So our first step is we want to start listening for mouse move events as soon as we receive a mouse down event. And then we want to keep listening for those events until we receive a mouse up event, at which point we say that's what constitutes our drag event, and we can emit that value on the stream down here. So just looking at the structure of this problem, we're probably going to need 2 operations. Something to tell us to start listening for mouse moves, and then something to tell us when we should stop listening. So the first operator we're going to use is something called a concat. And don't worry about the exact details of all these operators. Really tonight, just like focus on the structures of what these, like how to solve these problems, and then what the solution actually looks like. So what concat is going to do is, given a mouse down event, it's going to tell us to start listening for mouse move events. You can see down here in the bottom right the code that we would use to model this. But we don't just want to start listening for mouse move events. We want to do something a little bit smarter. We want to listen for mouse move events until we get a mouse up event. And so to do that, we're going to use an operator as called takeUntil. And what takeUntil does is it's an operator which takes in 2 streams. In this case, our mouse move stream and our mouse up stream. And what it's going to do is it's going to listen for mouse move events until we get a mouse up event. And at that point, it's going to emit a value on our drag stream. Okay. Here's what all the code is for that in one place, so it's a little bit easier to read. Lines 2, 3, and 4 just set up our streams. On line 6, we actually compose our drag event from our primitive streams. And then on line 10, we actually subscribe to our drag event to start consuming data for it. Observables are what are known as lazily executed structures, so they don't actually really start running anything until you subscribe to them. So we're going to see more on that later. I'm going to have a little demo. Okay, so we've seen that Rxjs can help us do some pretty cool stuff, right? But it does have a learning curve, or as this Twitter user pointed out more specifically, it has a learning cliff. My favorite part of this tweet is the timestamp, which I just noticed. It's at 2:03 a.m. So just imagine like this poor guy is trying to debug his Rxjs code at 2 in the morning. But it's true. I mean, it can be very overwhelming the first time you learn it for two reasons. Number one, this reactive style of programming is difficult to wrap your head around when you first see it. And number two, the API for Rxjs is pretty intimidating. Like I mentioned, it has map and filter like arrays, but it actually has many more operators than that. Specifically, it has like 50 plus more operators than that. And I don't know, to me the first time I saw it, it just felt like getting broadsided by a bus. But the good news is, for like 95% of the code you're gonna write with Rxjs, you'll use like 7 of these. I mean, you'll use map, filter, take until, interval, and a couple of others. Occasionally, you get to do something that's like really, really overpowered, like expand, which lets you do recursion on observables. And if there's enough time tonight, I'll show an example of that. But the good news is we're not going to focus on the API tonight. We're just going to try to build an intuition for how to use it. So before, when I asked how many of you had worked with Rxjs, I think maybe half the room raised their hand. But for the half of you that didn't, like how comfortable are you with arrays? Just working with arrays in JavaScript. Okay. So the good news is you actually probably already know some Rxjs. You just might not know that you know it. Before I mentioned that a lot of the intuition you have from working with arrays can be transferred over directly. And the reason for that is because there's actually kind of a deeper symmetry here between the iterator pattern, which covers arrays, and the observer pattern, which would constitute observables. So has anyone worked with these patterns before or has heard of these before? Observer and iterator? Okay. Well, they're kind of two sides of the same coin. So both of these patterns deal with situations where you have a producer of data and a consumer of data. And the difference is iterators deal with pull streams. And in those situations, you have a consumer of data pulling data from the producer. Okay? Whereas with an observer, it defines what's called a push stream. And in that situation, a consumer of data will give its producer some callback whenever it has data, and then the producer is actually pushing values out to the consumer. So this is perhaps best illustrated with an example. Arrays are a great example of an iterable. And we all know that you can access values in an array by passing in an index, right? Array of 0 or array of 1. What you might not have known is, starting with ES6, you can also get something which is called an iterator, and use that iterator object to step through the values in an array. And what this looks like is iterator is just an object which has a next method on it. And each time you call next, it'll get you the next value out of the array, which it stores in this value property. And then it also has this boolean called done. And what done is it's a way for the producer to signal to the consumer, I don't have any more data. And you can step through all the contents of an array simply by calling next. The last time you call next, you'll see that we get a value undefined because there's no more data, and done has been set to true. Okay? So when you work with iterators for pull streams, they basically specify 3 things. They will give you a way to consume data, which is this value property. There's a way for the producer to tell the consumer that there's no more data, which is this done property. And in the event of an error, usually the producer will just throw an error that you can patch. So why would we waste our time using something like an iterator instead of just accessing the values of an array, using like array of 0 or array of 1? Does anyone have a guess? Well, think of it this way. What if you want to consume data from things other than arrays, other types of pull strings? there could be many producers of data, but like we have arrays, strings, maps, some arbitrary data type that you just found in your legacy code base, right? Like there's lots of things we might want to pull data from. And we'd like to be able to use language features like for-of loops or the spread operator to pull data from all these producers without having to like learn their APIs or their implementation details. So that's why we use something, we just use an interface, which is the iterator that we saw on the last slide. But the other side of this problem I was talking about, push stream, it defines a way of telling the consumer that there's no more data, and it also defines a way of communicating errors with the consumer. But notice that conventionally in JavaScript, when we work with push streams, we don't have two of those things. When you set up an event listener, you just give it a single callback for onNext. There's not really a way for this code to communicate to its consumers that an error has occurred or that there's no more data. And this is because back in the 90s, when JavaScript was being written, the main source of events were just DOM events. And there's not really a notion of completion or error in that context. Usually consumers just wanted the next piece of data. But today we work with all sorts of event streams, some of which might error, some of which might terminate. And so the solution to this problem is the observable class provided by Rxjs. That provides a common way for consumers to receive data from push streams. So in depth, what that looks like is you've got some underlying data stream. This could be DOM events, could be XHR requests. We've abstracted away the implementation details of that stream inside of an observable. Okay? And then what an observer does is it simply calls the subscribe method on that observable, and it passes it 3 functions this time instead of 1. It passes it onNext, onError, and onCompleted. And what the observable will do is it responds with an object containing an unsubscribe method, and that's just a way for the consumer in this push stream to say, I don't want to receive any more data. You don't need that in the iterator because it's the consumer that's pulling data, so it's the consumer that's in control. But with push streams, it's the producer that's in control. And then each time data comes in on your stream, the observable just calls its observer's onNext method. If it ever runs out of data, if this is a finite stream, let's say, maybe a sequence of XHR requests, it'll call onCompleted. And if an error ever occurs, it calls onError. So using that, let's build a search box. You may remember this from last time. I got about halfway through the code and then kind of had to rush it towards the end. So let's go over this in a little more detail. So we want to build that search box that we saw on Apple's site, right? But we're going to do a Pokemon themed one because that's a little more entertaining. And it has more Pikachu. Just like to point out, when I was a kid, the Surfing Pikachu was by far my favorite card. I could never find it. He just looks so happy he's catching her. Okay, so let's build this. So what are our requirements for building this type of search box? By the way, I should note that we're going to make this so that whenever a user starts typing, we hit an API and pull down all of the cards that contain what they've typed as a substring. And we want to do this each time the user types something, so we want this to be very reactive. So what do our requirements look like? Well, we want to be able to listen for keystrokes. Okay? Each time the user types, we want to know that they've typed something. And each time they type, we want to send a new XHR request to a server. Okay? Because we want to pull down data each time they type. For performance reasons and for better usability, we want to add a 250 millisecond delay before sending out XHR requests. And so what that looks like is if a user types something like they're searching for Pikachu and they type PI, but they type it really close together like PI, we want to count that as one request. We don't want to make 2 separate requests in that situation. And then last but not least, we need to make sure that we're displaying only the latest search results to the user. Because if they're searching for Pikachu and they type it like PIKACHU, that's going to be 3 separate requests that we've sent to our API. But like, we don't have any guarantee the order that these requests are going to come back, right? Because they're going over a network. Packets could get dropped, they could come back out of order. So we need some way in our solution to make sure that we're displaying only the latest search results. So take a second and think about how you would write this today using callbacks or promises or whatever your weapon of choice is when it comes to doing async programming. And just try to get an estimate of like how many lines of code you think it would be. So let's start by identifying what our input stream is going to be. In this case, it's just going to be whenever the user types in the search box, right? That's where we're getting our inputs from. So we're going to use that, we're going to model that using from event, which is what we saw way back in the drag and drop example. So here we're just passing the search box as a reference, and we're listening for input events on it. And for this particular example, the user is going to be searching for Pikachu. Now our next step is, each time the user types something, we want to actually take that and send it off to a server to pull down data based on what they've typed. So we're going to use something, in this case we're just going to use a map. And what map is going to do is it's going to take each keystroke and map it to an XHR request, okay? But there's actually kind of a subtle bug in this code. Can anyone spot it?
No delay.
What's that?
No delay.
So we're going to add the delay in just a couple of slides. But good catch. Okay. So map on an array, when you call map on an array, what is its return type?
Single value.
So when you call map on an array, you'll always get an array back.
I'm so sorry.
Yeah, no, it's fine. Well, it's the same with observables. When you call map on an observable, you always get an observable back, right? You have to be able to make sure you're always returning observables, otherwise you won't be able to compose them together with chaining. But in this particular example, inside of our map, which we know is returning an observable, we're making an AJAX request, right? We're trying to pull some data down from a web API. Well, that in itself is an asynchronous request, so that is also going to be mapped or wrapped inside of an observable. So in this case, we actually have a two-dimensional observable, which, if you've ever worked with arrays and you've like done some mapping and found yourself with a two-dimensional array structure, can be problematic. So in this case, we'd like to have something that'll actually flatten out those responses so that we can just receive the card data as opposed to the card data still wrapped inside of an observable. And this is a situation where if you were doing this at work, you'd go back to that giant list of operators that I had before and try to find one that'll do flattening for you. So in this case, we can use something called a concat map. And what concat map will do is it'll still map each keystroke to an XHR request, but then it'll flatten out those XHR requests before it emits any data. So that way we can have direct access to the results of those requests. Another nice thing about concat map is it will ensure that whenever we make a single request, we always get that data back first. So concat map will ensure that we're only displaying the latest results to the user. But really, whenever somebody types, we don't care about any of their previous searches, right? We only want to really fetch the results for the most recent search they've done. So there's actually a different operator we can use, which is called switch map. And what switch map will do is each time a new keystroke a new input event comes in, it will just cancel any previous XHR requests that we had made. Okay. So at this point, we've got 3 of our 4 requirements. We're listening for inputs. We're mapping those inputs to requests to our API so we can pull down the latest data, or so we can pull down data, excuse me. And then for switch map, we're making sure that we only display the latest data to the user. So what was our 4th thing? It was the 250 millisecond delay, right? With that, we're going to use an operator which is called the bounce time. And what the bounce time does is you pass it some argument, in this case 250, that's 250 milliseconds. And what it'll do is, when it's listening for keystrokes, it'll wait for 250 milliseconds of silence before it actually emits a new value. Okay? So here, if P and I are typed very close together, the bounce time will turn that into 1 value, so we'll only make 1 request instead of 2. And in this particular case, that's really just more of like a performance optimization than anything else. Okay. So, that's it. That's all the lines of code that we need to build a search box like this. The only thing left to do would be to subscribe to it. Down here, we pass it on next, on error, and on completed. Whenever we get data, we want to display those results to the user. If we get an error, everything catches on fire. And then, honestly, on completed is almost always left empty or just omitted entirely. It's not something that people usually use. If you want to play around with this example, I've put it up on Stackblitz, and I think I have a really poor quality GIF coming up. Yes. So this is what it looks like. Is when you type, I think I'm searching for Hitmonchan here, you'll see it's going to pull down the card data each time the user types. Okay. So I'm a little bit ahead of schedule, it looks like. Before I go to the last example, are there any questions on this so far? Yeah.
Why 215?
Arbitrary choice in this case. That's
Is it a common use number?
That's what I've seen in examples. You don't want something too low because you want to give people a chance to type, but you also don't want anything too long because then you're just kind of wasting time, right? Okay. Yeah. Any other questions so far before I go into the last example? Yes.
Operator for mapping request and response for an API call.
I'm sorry, what's that?
Suppose we are making multiple API calls in a loop.
Yes.
So if I want to map the request to the responses, so what would be the best operator?
So funny you should ask that. Because when you're making multiple API calls, you can use the operator I mentioned before called expand, which lets you do recursion on those. And we're actually going to see an example of that right now, okay? Anything else? Okay. So for this last example, I hesitate to say that it's like the most complicated example, but it is sort of complicated. What expand lets you do is it lets you do recursion on observables, right? And we're actually, well, we can go over this briefly. It's not too important, but what expand does is you give it some input stream, just like you would for any operator. And anytime a value comes in on that string, it immediately emits it to its output stream. Okay, so it mirrors its source. But expand also takes a projection function just like map did, but this projection function can be recursive. So in this case, what we're doing is we're checking to see if the input is equal to 8. If it is equal to 8, we're returning an empty observable, which will just break us out of our recursion. It's basically our base case. Since we're doing recursion, we don't want to blow up the call stack and go on forever. If it's not, then we're going to produce this new observable here, which is 2 times whatever value we gave it. And so this is probably like the world's most complicated way of producing the first 4 powers of 2. But you get the idea. Let's see a more realistic use case. A lot of times, expand can be used whenever you want to consume paginated data from an API. And the example that I'm going to show you comes from a great article written by Nicholas Jameson called Rxjs Understanding Expand. So if you want to learn more about this stuff, I recommend checking out this article. And I have a slide of resources at the end of this talk as well. Okay, so let's consume some paginated data. So for this example, we're going to consume the GitHub API. And what we want to do is, given a user, we want to get all of the repositories associated with that user. But the reason we need pagination is because a user can have multiple repositories, right? In this particular example, I think this user has over 900 repositories, which is kind of crazy. So obviously, GitHub can't send you all that data in one response, right? It would be too much to fit into a single response. So what it will do is when you get the response back, GitHub will usually put like the first 30 repositories in the body of the response. And then in the header, it will give you some pagination information. And in GitHub's case, they put all of the paginated data inside of the link header. Okay. Has anyone here worked with consuming paginated APIs before? Okay, a couple of you. Cool. So all this says is, you've got the first 30 repositories, let's say. If you want to get the next 30, go to this URL here. And you know that because it says next. And then GitHub also provides the URL to the last 30. In this case, you can see that it takes 33 separate pages to deliver all 900 plus of this user's repositories. So in order to solve this problem, we're going to need a couple of helper functions. Number one, we're going to need something that can parse the response header and see if we've got a URL, if we need to basically make another request. So don't worry too much about what this is doing. I'll just briefly summarize it for you. You pass it in a response. It's going to get the link header out of that response, and then it's going to check to see if it contains basically a URL for the next page of data. If so, it returns that string. If not, it'll just return null, indicating that there's no more paginated data. We have one other helper function called get, which, given a URL, is actually going to make a request to GitHub's API and consume the data at that URL. The only difference here is, just as an optimization, we're going to do this mapping operation here. Because a response can have a lot of information, really we're just interested in the content of that response, which is the user's repositories. And then here, this is how we do pagination. We're going to take the response and pass it into the next function, which is what we just had on screen. And if there is more paginated data, next is going to point to that URL. Otherwise, it will just be null. So now comes the fun part. We have our URL, and we make a GET request to it. A single request goes out, comes back. We now have 30 repositories for this user. Okay, but we want to make sure we can consume paginated data as well, so we pipe it through expand. And what expand is going to do in this case is it's going to take the response and it's going to check to see if that next field was set. So in the case where there is more paginated data, next is going to be the URL. And in the case where there is no more paginated data, it's going to be set to null. So when we do have a URL, this is the recursive part. We call that get function that we just wrote, which will issue another request. And if there is no more paginated data, we'll call empty. Empty just returns an empty observable. So thinking back to that diagram before, it's not going to produce any data. It's just going to call onCompleted immediately. It's kind of like wrapping the null value inside of an observable. And in doing that, we're going to keep recursing and consuming this paginated data until we run out. So this code right here will actually let you consume, well, this plus the code on the other two slides will let you consume all of the paginated data from the GitHub API. So I do have an example of that as well at the Stack Blitz. I think, actually, I might just show a live demo of that since I still have a few minutes here. Let's see if I can get away with this. See if the live demo gods are feeling friendly today. Okay, and I'm going to go ahead and pull up the network tools so you can actually see it. So now if I go ahead and click on Get Paginated Data, you're going to see we make a request. You can see here it's actually going through and consuming each page of data from their API. And if I could scroll fast enough, you can see we keep adding all of the repositories. Okay. Okay. Cool. That's actually all I've got for this talk. Here's a list of resources. The first one points to the blog series I've written. So if you want to learn more about this stuff in depth, if you want to actually see how to implement an observable type from scratch, just to convince yourself that there's not really any magic going on there, strongly recommend checking that out. If you have any questions about this stuff, feel free to hit me up on Twitter. I love talking about Rxjs. And yeah, with that, I'd like to take any questions. Gonna need a napkin for that.
Any questions?
Actually, I have one.
Yes.
So from this, maybe these two examples, I can't see the advantage of Rxjs over the promises.
Okay.
So you say the promises only one future state, but how is observable can have like multiple future states?
Right, exactly. So if we were using promises, let's go back to this example here. This one's a little bit easier. If we were using promises, we would need, first of all, we would need to create a new promise for each request that we're making out to the API, right? And we'd also need some way of mapping each one of these keystrokes, whenever the user types, to that promise, right? So you could totally do it using promises, but what you'll find is when you use observables, we've just created one stream here, one observable, and that models all of the user's inputs, right? Each time they type in that search box. So that is one example of multiple future values, right? Because a user typing is technically an asynchronous action. We don't know when they're going to type. And then each one of these XHR requests is itself going to be asynchronous. So you could use promises, but the benefit of using observables here is it's really just this one line of code here, right? And that is what's letting you make a new XHR request each time the user types. So for very simple scenarios, observables can kind of be overkill, but whenever you have something a little bit more complicated, like I want to listen for events, and then I want to wait 250 milliseconds, and then I want to make an XHR request, and then I want to make sure I'm only getting the most recent XHR request, that's where having this ability to work with observables and kind of compose these pipelines becomes a lot of, like, a pretty big advantage. You can think of them as like kind of more powerful promises. There's actually a to promise and a from promise. No, there's from promise. I think there's to promise as well. So a great first step for working with observables is...
Yeah, I'll just leave you at that. I think that says a lot about his personality. And without further ado, here's Tsubasa.
Okay, guys. I'll just start off with an introduction. Hi, guys. I'm Tsubasa. I've been working as a IT consultant, technical-related sales, technical support for a while now, doing some also management leadership work in my small startup in Shibuya. Recently, I've been really excited about full-stack web development. It's really cool that you can make an app and then deploy it, and then here's this thing that everybody can use, and you just built it yourself. So if you can do something that's powerful, meaningful, and you can just do it all by yourself, right? So that's what I'm really excited about. That's why I'm here in the school, and it also excites me particularly about this technology, IPFS. That's why. Given that I have to do this tech talk, I thought, okay, here's something that's completely new and completely is radical technology. So let's get into this. That's what I thought. Yeah. So the goal for today is I want you guys to be able to understand why this is happening. Why is distributed computing? Why is decentralized computing becoming important? And why is it getting interesting? And also, I want to do some hands-on demos. And then I feel like it'll be so easy that you guys will be able to start contributing, start using this new technology called IPFS. Prerequisites. This will be tailored towards people who are familiar with computer science, who have been a dev for a couple of years. Specifically, you need to understand what the HTTP protocol does. You need to be able to understand what I'm doing in the terminal or Bash. And also, I'll be doing some JavaScript. So if you have trouble following along, please feel free to raise hands, ask questions. I have set aside time to make sure that this is interactive. Oh, also I like your enthusiasm, so stick along. I appreciate positive energy and stuff. Okay. Yeah, and also, yeah, if anybody has a computer and wants to follow along, I empower them to do so. We'll be starting off with just these 3 prerequisites for the time being. So I don't see any computers at the moment, so I guess that's not so much of a. Okay. All right. Just a breakdown of what I'm going to talk about today. First off, I'd like to go over the issues that HTTP, the protocol that IPFS aims to replace, is facing today. And then I'd like to do a simple demo and then deconstruct what IPFS does. And then I'd like to also go over the caveats of the IPFS ecosystem right now. Okay, so HTTP has some problems. So who is familiar with the HTTP protocol? Obviously. So essentially, this is one of the protocols that consists of what is loosely and casually called the Internet Protocol, right? All of these protocols come together to form what the Internet is today, right? And the Internet has completely changed the way we live life, right? The way we eat, Uber Eats, the way we do banking, all of our online banking. So really, it has changed the way we live, and it's thanks to all of these protocols and the people who have designed them. But the internet has changed over the past 2 decades, and so there's problems that HTTP has to face today that it wasn't designed for. Okay, so specifically, I'm going to break it down into 3 components: efficiency, resilience, and ownership. So efficiency. So Juan Bennett is the guy who created IPFS, and he discusses and identifies these problems no better than anybody else can, actually. So I'm going to straight up cop off of his presentation slides. That's one in the bottom right corner. And first off, we're going to talk about latency. Okay, so that's a URL up on top. And obviously, you have a DNS service that would resolve that into an IP address. What is an IP address? It's something that designates a location, right? This server is located at this address. And this number allows you to route through the IP network to actually find the server and then get the PNG that you want. The problem is that this server could be anywhere, right? Let's say this is just some dude hosting a server in Europe, then you have to, if you're in Japan, make a request and it will traverse all the way across the internet to Europe, also going through either Russia or America. I guess in this example, from Japan to Europe, you have to traverse all the way through these fiber optic cables that are running alongside the African continent. Tell me if anybody's into this kind of level of infrastructure. I might be wrong. So this is the situation here. Let's say that all of these servers have the exactly same content, and maybe somebody in this room has this. Even if that's the case, I'll have to go all the way to Europe to get that file. And essentially, that takes time, right? And that is latency. It takes time to go all the way to Europe and then get that file back. And this becomes a problem with, real-time apps, for example. Let's say with Google Docs, you're editing something. If that server is, again, in Europe, and then somebody's editing in another part of the internet network, let's say he's in Africa or something, then you will have some latency. And it will be difficult to be collaborating in a real-time manner because you have this server architecture. Bandwidth. So let's say, again, we're in a classroom. We have like 30 people. I have a dank meme that I want to share with everyone. In which case, what would happen is you have 30 separate requests going through the network all the way to a server somewhere, YouTube, and it would have to return all of that back, right? And you're eating up a lot of bandwidth to get the exact same content. So yeah, latency. Also, problems with resilience. So this is Kanye West's one of his earlier albums. This is when he was personally at his artistic peak. There's a lot of breadth in the expression that he has in this album. And it's called 808s and Heartbreak, and I want to talk about 404s and Heartbreak. Yeah, resilience. So we have that example just earlier, right? Google Docs. Let's say Google Docs is down. Then all of a sudden, you cannot do anything. It's almost funny, right? A couple of years ago, it would have been the norm that everybody has Microsoft Word. And so there doesn't need to be a server. You can just write it and save. But now that everybody's on Google Docs, actually, when the server is down, you literally cannot do anything. You can't even write a single letter. This is painful. This is a bad idea. And in differing scales of that, of what you cannot do with that failure, essentially all of the recent apps that we use in our lives are essentially have that same infrastructure. If it goes down, you cannot use it. Developers, this is familiar, right? Somebody moved the repo, they renamed the repo, and then over time it expired. Pink Unicorn, I love this guy. I see him maybe a couple of times a year, but don't want to see him still. And it's not just a problem with GitHub, clearly. This is just a problem of the way things are, fail whale. And this makes Kanye very upset that he cannot make his controversial tweets. And of course, it's not just a problem of web services being unavailable. Sometimes you're on a plane and they don't have access to the rest of the network. If you're in the U.S., then sometimes you have ISP outages, or you just have straight up data center physical failures like fire. Yeah, this is a single point of failure, and it's also prone to blocking. Let me go over this in the next section, ownership. So yeah, we just mentioned how earlier things could fail in this sense, and let's talk about Turkey. That Turkey. Specifically, there was this incident. I'm not quite sure when it was. There was an incident in which there was a controversial Wikipedia article in Turkish on the Turkish Wikipedia. That was unfavorable to the government at the time. And so what they did was they said, this incites terrorism. This content incites terrorism. And so they blocked the entirety of the Turkish Wikipedia inside of Turkey. They shut it down. And so you have a government who is able to do that. They are able to restrict access to information. And this isn't a problem, again, with Turkey. You have Egypt, and also you have a whole bunch of other countries with questionable human rights records who are blocking things on the internet. And so the question becomes, who owns the internet? Who's supposed to have control of the internet, right? And the reality of it is actually depicted really well by this guy called Scott Galloway. He's a professor, head of marketing in NYU, and he has really the right idea in terms of hairstyle, and also the presence of what's happening in big tech today. So, yeah, a decade ago, these were the largest companies in the world. And now, actually, the case is that they have been dwarfed by these big tech companies. And it's not just a dwarfing in economic scale. It's also dwarfing in how many people these companies have as an audience. So Apple has 1 billion paid customers. So that they have 1 billion accounts in Apple Pay, for their music, their apps, etc. This is the Catholic Church. The Catholic Church has 1 billion registered members. and Facebook has 2.4 billion users. So in a strange sense, Mark Zuckerberg has more reach than the Pope. That's the scale that we're at today. And it's not just a problem of how big it is, it's also a problem of, this is changing how society works, this is changing how politics work, right? Back when we had the 2016 presidential election, we had a lot of traffic going into fake news sites because you could engineer that. And Facebook did nothing to stop this, right? And also, of course, digital ad spending, huge market, and the majority is being eaten up by these huge companies. So this is usually, it's like a 40-minute talk by Professor Galloway. Very interesting stuff, very insightful. I highly recommend that you take a look at it. I'm not going to go into detail further. And it's not a problem that these big tech companies are bad. It's a problem of, the basic tenet of capitalism is that you have a healthy marketplace. And clearly, you see a lot of symptoms that's saying this is not a healthy marketplace. You have way too many big players. These four players, for example, together their market value is larger than the GDP of France. There's also other problems. There's a whole bunch of problems. I'm going to start speeding up over here. But Ajit Pai is repealing net neutrality, right? And what net neutrality does is, it usually gives you, fair, equal bandwidth for all of the services that you do. But instead, it's been repealed, so potentially service providers could do things like block things outright, or say you have to pay this much money to access Netflix, this much money to access Wikipedia. And this isn't just a problem, for a small minority of people. This is a map of all the areas where there's only one single ISP. So if an ISP does something restrictive like this, you won't be able to change to get access. You're living in a monopoly. And this is, a small article I saw recently, where a fire department was responding to a major wildfire, and their data bandwidth got throttled when they were trying to respond to this situation, and their command and control was affected by this kind of throttling. It shouldn't be happening. Then there's PRISM. This is a CIA, NSA operation where they're actually listening in onto all of the traffic that's going through the infrastructure of the internet. Very interesting stuff. So partially because of centralization, there's a lot of these things happening, and it's because the ownership of all this major infrastructure is owned by these large companies. And I feel like, if we start taking ownership, conversely, the way it was back in the beginning of the internet, we'd be able to diminish these issues. So HTTP has issues. And in a larger sense, the internet has problems today. And so IPFS is a technology that is one of the solutions to the problem, I believe. So IPFS is a distributed protocol. What it does specifically is, it's a peer-to-peer distributed file system. That's a little difficult to understand. So in layman terms, it's a collection of file directories, and it's almost like you have a hard drive called the internet, and then everybody who accesses it, you can access the same files. And it's distributed, so essentially you don't have a server. All of the files are hosted on your machine and the other person's machine, and essentially on everybody's machine. I could go over the technological details first, but I think it's best if I just show you what you can do currently. So let's get to it. Okay. So obviously, I usually don't have it on the desktop, but I'm just going to keep it on the desktop for simplicity's sake at the moment. Oh, that's interesting. Excuse me. Okay. So if you've done the prerequisites earlier, then you would have done npm install global IPFS. This takes a little bit of time, but I'm not going to do this. But essentially, you do this, and then you will have the JavaScript version of IPFS installed. And then, if you do this, then your IPFS node will initialize. When I say node, essentially, you're a node in a graph. And the graph is, again, the IPFS network. And here you have pure identity. So this hash represents who you are. This is the hash that represents your node. And here you are. You can already start accessing the network and getting content. Unfortunately, this command is incorrect, so you have to fix it. But there you go. You just got a file from the IPFS network. So this required no connection via HTTP. And it's a simple IPFS README. Let's try to add something to the IPFS network. Sorry, is this readable for everyone? Should I make it bigger? Enhance? Enhance. Enhance. Okay. Okay. Perfect. So we have this ASCII art. Who's familiar with what cat does? Go ahead.
It just shows text file.
Yeah, perfect. Yes. So here's that. So yeah, it's ASCII art. It's just text that looks like a picture. Yeah. Okay. So what I can do. JS IPFS add. Not bad. Not text. So I just added a file to the network, and essentially, if you don't have a daemon running, then it's not going to actually serve. So let's do that. Great. So we have a daemon running in this terminal, so I'm just going to run up another instance. I'm going to enhance that one as well. Maybe it's a little more pleasant if I keep it top and bottom. So now what I can do is I can recall that same file from the network. So JS IPFS has its own version of cat, and essentially what it does is it retrieves a file and then you can pipe it into a text file or whatnot. So I need to copy and paste this hash. And then maybe I'll pipe it into okay. So I've taken this file from the IPFS network and then I've retrieved it locally into a file called retrievednb.txt. And let's see if we got it actually. Yes, we did. There you go. Not bad at all. Okay, so this seems less immediately apparent that you actually got a file that's served off of this completely new network. So we could do something similar on the front end. Bear with me. So also, there will be moments where I'll be doing things like installing, or moments of silence, and okay. Yeah, there might be moments of hanging or waiting for something. If you have a question, please feel free to ask the question. Okay, so this is, again, the repo for JS IPFS, and actually has a whole bunch of examples that are very interesting, very powerful already. So I'm just going to clone the repo. And honestly, this is going to take some time, so I've already downloaded this, and I'll just show that to you guys. There we go.
One second.
Uh-oh.
When in doubt,
Light's good.
turn it on, and then turn it off, and then turn it on.
Are there any questions so far? I'm doing some very basic stuff, but I think the concepts that are necessary to understand.
Okay.
Yeah, go ahead.
So you said this is a distributed system.
Yes.
I don't get how is it distributed. I mean, is this file stored on someone else's computer?
Okay, so essentially it's currently hosted on my computer.
Okay.
But again, this is a network, so if I add it on another, node in the network, then again, obviously it would store it, and then you'd be able to retrieve it peer-to-peer.
Oh, okay.
So it's a private distribution. It's all yours. It's not some anonymous person's.
So it's publicly accessible. Whoever's following along, they could also do exactly the same thing I just did and retrieve the file from my computer already at this moment. It's just a little difficult to have two separate devices.
Without specifying your hash.
Yeah. Oh, you have to specify the hash. But the hash is actually addressed to the content. It is not addressed to my machine. So, to give you an example of that, go into JS IPFS. Again, this is a repo I just cloned off of the official JS IPFS implementation. Typo. And then again, here in examples, there's a whole bunch of examples here. And as you can see, there's things we can do like produce readable streams, do some circuit relaying. I just want to show you the one example of exchange files in browser. Again, everything's in alpha, so it will throw you some angry warnings, but no errors, at least. So I'm just going to open this up in my favorite editor, VS Code. Who here is familiar with Node.js? Can I get a show of hands? Okay. Okay, I see like half. Okay, I'm just going to be very simple then. Package.json declares all the dependencies and also the execution points for Node.js. Specifically, all the dependencies and dependencies necessary to compile a file are declared here. And then in scripts, well, this is just something that this person has chosen to use, but you have the bundle script, which would compile or transpile everything so that it can be run in the front end. And then you have start, which actually starts the web server, so you can actually access it locally. Okay, so let's do npm run bundle, and then npm run start, and that would serve the web server with the content that I want. Here we are. What?
Actually, you can use Dapps. Actually, you want
Oh yeah. Whoops. Oh, I guess I got a typo. That's what it was. Okay, so now it's running, and I'm just going to open it up on my browser. Okay, so this is the front end, and this has no access to my file system. And essentially what I can do is I can take that hash that I had just earlier. I'm sorry, I'm just a little lost for a moment. Where did you go? Okay. Oh, small anecdote. So hashes are, cryptographic, so checksums. So if I add the exact same file to the network, then it will produce the exact same hash. That's what I mean when I say content address. If anybody's been paying attention so far, then you notice that the beginning, the entire hash is identical from what you just saw earlier. Okay. And I'm just going to take this to the front end and try to fetch a file. Yay. There we go. Okay. So again, IPFS is a peer-to-peer distributed file system. As you can see, you could easily exchange files between computers. And again, there was no server in place there, right? The server that was actually serving the page, the server didn't have any content inside. So by distributed, sorry, just to make sure that everyone's understanding this, a centralized system, which is what most conventional web services have today, is visually like this. You have the Facebook.com, Google.com, essentially. And essentially, if this server goes down, then all of these other nodes are dead in the water. Decentralized is something like Mastodon. You have multiple instances that talk to each other. So it's a bit more resilient to failure. And then distributed is where all the nodes are equally functioning and trading data to each other as equals. And that, in which case, it's as resilient as it gets. So just the earlier example we had earlier, if that dank meme was in Europe, I wouldn't have to go all the way to Europe actually. Since if everybody else had the same file, if there was somebody in this room who had that file, then you could actually retrieve it right off of that computer instead of the origin. So I just mentioned earlier what a hash is. So you give a hash function an input, and then it would change it into something called a hash, which is kind of like a fingerprint. It would give you this kind of collection of alphanumerical values, which are derived from the input, and it will always give you back the same output. And whenever you change something, let's say we change Fox into Fox with 2 X's or something, then the hash sum would be completely different. It would completely change. And so you're able to always check that this is the content from the hash. There's another concept that IPFS uses called DAG, or Directed Acyclic Graph. Who's familiar with Directed Acyclic Graphs? Anybody? Okay. Gentleman in the black.
It's a graph that has directed edges. So the edges have an arrow, and they are also.
Yeah.
So you can never run. If you follow the arrows, you can never like circle around. If you just go somewhere and follow the arrows, you will stop at somewhere.
Exactly. Yes. So IPFS uses this particular data structure, and they combine it with what we just mentioned earlier, hashes. And they have this together. This technology is called a Merkle DAG. Essentially, you have a directory, right? And a directory is a tree, you would think, but let's say you have two of the exact same files in a separate location of the directory. With a DAG, then you're able to say, okay, these nodes go together. And so it's called a Merkle DAG. Sorry, wrong Merkle. Wrong Merkle. Merkle DAG is, again, this data structure which expresses a directory. And also, it's also able to express the versioning of the data structure, of the directory. It's just exactly the same thing that we use with Git. You have a hash that expresses what this file is, what this file is, what this file is, and then altogether the directory, including a file name, is given another hash. And so it's a tree of hashes. So that's just one of the basic concepts that consist of IPFS. IPFS is actually a whole suite of protocols, beginning, and this is the internet protocol, right? And in replacement of that, we have a whole, again, suite of protocols, starting from what I just mentioned earlier, which is IPLE, which has the Merkle DAG implemented. There's also IPNS, which allows for publishing and versioning of hashes. So you can have one URL, one hash, to which you can publish, kind of like deploying to the same address. There's a lot of technology here. I cannot explain all of them within the given time constraints. I'm just going to skip over this for the moment. Okay, here's another interesting demo that I can do. Okay, this is something that I've already built. It uses a combination of IPFS, IPFS PubSub room. PubSub is this concept where you have a IPFS hash. You have this node, not node. You have this content, and then it updates over time. So it's kind of like shared state if you subscribe to it, and that's exactly what PubSub does. And I have a very simple front end using Vue UX, and let's see if it works. So I'm just going to show you the console as it's firing up. So you can see that there's a hash over here, and that's the hash ID of this front-end node. And then you can see that it has a a rendezvous server at the moment. Oh, and there you go. I just have my phone running, and so I just have another node added to this. If anybody else also has Chrome or Firefox, they can also try opening this on their browsers. What I'm going to do is try to play some music. bear with me for a moment. I forgot. Of course, if you don't have two browsers, then you cannot really see what's happening between the two nodes. And yes, if you give it some time, you could see that peers displayed. And essentially, these front ends have been able to discover each other through the network. This one's taking a bit of time. Let's see what's happening here. Nope, that is not going to. Oh, there you go. That's strange. Okay. And just as a proof of concept, you can see this guy is QMQ. QMQQ8Y, okay, very easy to pronounce. And then this guy is, okay, so it sees that this guy is a Q, as a peer. And same goes here, QMBDMN. You're able to see that that is also identified as a peer here. And I also have my phone connected. That's what QMROSR is, I presume. Okay, let's play some music. So I just added a file, and then it was able to identify the audio source here as well. Now, once it's actually finished loading, it should display maximum time. Okay, it just did that here. Come on, you can do it. There you go. Okay. That's because it takes some time to traverse through the network. It's great. Yeah, so it does require some latency. Right now what's happening is that due to there being a NAT, it actually has to traverse pretty high up, pretty far through the IP network in order to actually converge and then do these communications. Check it out, feel free to do that. Okay, just to sum things up, HTTP has issues, and IPFS seeks to solve that, and it's a distributed peer-to-peer file system. Okay, there's some caveats to this technology. So as you just discovered right now, peer discovery and routing is very much a work in progress. Trying to implement a networking protocol in JavaScript in the front end is quite the feat, I believe. And yeah, punching through network address translation servers and also is difficult. And also yeah, just even without that, finding making a peer-to-peer connection is quite the challenge. They're trying to implement this thing called DHT also on the front end. They already have a backend implemented in Go for DHT, but for the front end, it's as you just saw earlier, it does take some time. It is a work in progress. Efficiency. Also, if anybody tried this on their phone for an extended amount of time, they will feel their phone heating up. It's not as performant as it should be. Also, there's no natively supported browsers yet. So when I said it would replace HTTP, I think the first place the place where people see HTTP the most is in their URL, right? And IPFS should be able to be there. It's a protocol that's able to address without HTTP at all. And currently there's no fully supported browsers to do that yet. However, Firefox has already said that in their alpha stage they will be supporting some of these distributed protocols, one specifically being IPFS. I'm not sure what Scuttlebutt is. Also, there's incentives for hosting. Like with BitTorrent, if you have something hosted for a certain amount of time, if you're just downloading something, and then during that time you're a host, that's great. But it doesn't make something available all the time, and there is no incentive currently for hosting that content. At this point, there's this new project that the creators of IPFS are working on right now called Filecoin, which is another cryptocurrency. It gives, it's actually for people who host content, they'll be able to mine cryptocurrency. So essentially, they're given essentially money to host content. Yes. Yes. We build the internet. We have the technology. We can make it better than it was before. We can make it better, stronger, and I believe faster. Thank you. Yeah, these are my social media handles. If anybody wants to get in touch with me, they're very much welcome to do so. I also have a whole bunch of references regarding all the spiel I had regarding how the internet is growing. Please feel free to take a look at that. I also have this presentation available, so please feel free to take a look at the whole thing. Yeah.
So this is only passive data, right?
Passive
so
as
it's
in-
just files that are distributed. Like if I wanted to write like a game, then I needed some place where like secret information is stored. That I need like some kind of server, I guess, so that not everybody can see the whole state of the game.
Okay. So you want some security or encryption? Is that what you're saying? Or you want to make?
I want a decentralized.
So he wants the files to be not visible to all people. Yes.
Yeah, exactly.
The visibility.
Yeah,
Okay.
you can do the encryption, right? But probably it's pretty slow.
Yeah, my colleagues also had the exact same question last week. And my answer to that is that I don't know. But I also have the intuition that it's a separation of concerns problem. For example, IP, that protocol has no security in mind. It's just at a lower level layer, and you're supposed to build security on top of it. There is no correct answer for this, I believe. But I feel like, yes, if you could build a layer on top of it for security, that is a solution to your problem.
How do you discover the peers? Is it also a single point of failure?
No, it organically, so if you could take a look at this statement. So it's looking at certain points in the network. It's broadcasting information at certain ports in certain parts of the network, and then it's able to, if there's anybody else who's also making the same calls, they're able to discover the peers.
So that connecting point is a single point, isn't it?
Sure. That would be like the Wi-Fi router here. So there are local points of failure, for sure.
How long would each hash last on the network?
The hashes last forever, actually.
So theoretically, you could upload your entire hard drive, just back it up on this.
Yes and no. That is to say, somebody has to be hosting it. Yes, somebody has to be hosting it, or else it will have a permanent address, but it will not be permanently available.
if I had like 10 gigabyte file on my node, will it be copied to all the nodes of the network?
So again, you have your node. If you host multiple nodes and then you add those, add them to the nodes, then it would be able to host those. For third-party, entities, if they access your content, then they will automatically start hosting. And that's one natural incentive that if there's something that's popular, then everybody would be hosting it because everybody would be accessing it.
All right, so I want to introduce Michael Arnold here, all the way from Berlin, to talk about getting started with building Dapps on Ethereum.
Cool. Thank you, Jan. It's been a long day, so if you want, you can stretch a little and get ready for the last talk of today. This is going to be packed, a lot of information, so bear with me. So I'm going to talk about getting started with Dapps on Ethereum. It stands for Decentralized Apps. Yeah, just come in. That's fine. It stands for Decentralized Apps. So quick show of hands. Who has heard of CryptoKitties? Or maybe even owns a kitty. I do own two. I regret it. So this is one of the, I would say, the first major decentralized app that saw some major traction. What you could do there is you buy cats, you sell cats, you breed cats on the Ethereum blockchain. The interesting thing here is every single cat of that had a unique hash basically attached to that cat, so it's like a collectible, so to speak. And they increase in price the more demand came in. Yeah, some numbers here. There's a TechCrunch article from 4th of December last year. People spent over 1 million USD buying virtual cats on the blockchain. Kind of nuts. I was one of them. I just so regret that. Anyways, so I'm going to talk today about how to build this, how you can build it yourself, how you can get started building a decentralized app like this. Destin, comment. First of all, I'm going to talk a little about myself. Who am I? Where do I come from? So I have a background with about, I would say, 4 years in startups. The first stunt I've done was at NeoReach, an early stage influencer marketing platform that I joined as a first hire after the founding team. We literally took the company from a dorm room at Stanford to 3 million annual revenues after 2 years. So that was an interesting journey. Then I packed my bags, flew from San Francisco to Berlin to start a company called Patron GG. GG stands for good game. Anyone who is a gamer knows that, hopefully. So this was the market that we're in. It was in esports. So we work with, so this is competitive gaming basically. There are gamers sitting here and they play in a stadium like this. It was an interesting journey. It was for about 2 years. So we built a mobile app to basically build for like esports fans to build a platform for them. And yeah, started the company alone, got some money, put the team together, launched a product. Eventually, things didn't turn out as I wanted to, so I sold my shares and then moved to Tokyo to join Chrysalis. Today, I'm not going to talk about this. We're going to talk about this, Ethereum. Quick show of hands. Who has heard about Ethereum and knows what it is? Great. So who has heard about Bitcoin? Probably most people have heard about Bitcoin. Bitcoin is one of, I would say, a bunch of cryptocurrency or blockchain projects. Ethereum is another one of them. Today we're not going to talk about Bitcoin at all. We're not going to talk about prices. We will not talk about, I don't know, let's say bubbles. Do I think it's a bubble? Yes, I still think it's a bubble. So we get that out of the way. Yeah, we're going to talk about how to build something on the Ethereum blockchain. And I try to stay on the surface of what the blockchain actually is and try to dive deep into the actual code of how to deploy a smart contract, how to write your first full stack decentralized app, so to speak. So bear with me. It's going to be packed with information. It might get overwhelming at some point, but it's good because it means you're learning. First of all, you're going to start with the internet is broken. Tsubasa gave good amount of information why that is the case, so we're not going to spend much time on this. I don't know what those algorithms are. I wish I could see what they optimize for so that I know it better, basically. Next one, paying for trust. Let's say there's a middleman like eBay or let's say Uber, Airbnb. They are the middleman in a peer-to-peer transaction. And the reason why they exist is could be convenience, but it's also trust and security. So basically they make sure that this person that sells it to you is a trustworthy person, you get what you're buying basically. They take a good cut for this, which makes it overall more inefficient compared to a pure peer-to-peer transaction because they take an 8% cut, I think is eBay. Yeah. Next one, data monopoly. So most companies store their data on all the big cloud storage servers, and there's two problems with this. The first one is you have a single point of failure. If something breaks there or messes up, your whole thing is down. Tsubasa touched on this. The second one is, Tsubasa touched on this as well, all those big tech companies have a bunch of information. So they're data monopolies and they can do a bunch of interesting stuff with this, if you want it or not. 2 days ago or 3 days ago was on the news that Google bought data from MasterCard and used that data to basically target you with ads. And I know for sure that Facebook is also doing some similar data brokerage things to target you with ads there. But I'm not going to go too deep into this. That would be out of scope here. A potential solution to this is, or could be, the Ethereum blockchain. So first of all, what is Ethereum? This is taken from the website, so take this, especially this thing, with a grain of salt. Ethereum is a decentralized platform that runs smart contracts, which are applications that run exactly as programmed without any possibility of downtime, censorship, fraud, or third-party interference. I highlighted two things, decentralized platform and smart contracts. So we're going to talk about what these two things are, and then, all the other things hopefully become more clear. I just want to get an understanding of the room. Who does not know what a blockchain is? So it's absolutely no clue. And it's totally fine if you raise your hand. Okay. Brought an apple. I'll make it really, really simple. I'm not going to go too deep into blockchains, but I'm explaining to you as if you were 5. This is an apple. I have one apple now. What's your name?
Samson.
Say again?
Samson.
Samson. So I have an apple. Samson has 0 apples, right? So right now I give this apple to Samson. So he has now 1 apple. I have 0 apples. That's the current state, right? So I now know that I have 0 and you have 1, and you know that you have 1 and I have 0s. All you who have looked and seen this also knows this. Let's just say someone comes in from outside and this person doesn't really know, and I could go to this person and say, hey, I'm going to sell you an apple, although I don't have anything, but this person doesn't know. And then this person would say, yeah, sure, and that's a problem, right? So let's revert this transaction. Okay, second scenario. I have an apple, you have 0. Let's keep all track of how many apples every single person in the room has. So let's say everyone owns a document that has on their phone with every single person's name and count of apples, basically, okay? So I'm gonna give you an apple now. So all our, let's call it ledger, well, let's just call it piece of paper. So the piece of paper has now the information that I have 0 and you have 1, so this has been updated now. That's the current state. Every single person has access to this. Let's say this person comes in. Great timing. Please feel free to sit in the front. So what do you think how many apples I have? It's fine, you don't know. So let's pretend you had this list that we just talked about, and he could just pull out his phone and see, oh, Michael has 0 apples. I'm not going to buy an apple from you. So this is referred to as the double spending problem. I'm not going to go too deep into this. But this is the basic idea of the blockchain, that there's a, let's say every person is a node, so a person in the decentralized network, or distributed network, similar to IPFS with Tsubasa. And we all have that piece of information. And if I were to fake this and say I have 100 apples all of a sudden, you all know that this is wrong, and then this information gets disregarded. And yeah, so and also what's interesting to note in the blockchain is that you can't really fake past information, so the state is mutable, and every time something changes, or a change of transaction or something, it gets added to the blockchain in terms of a block. That's why it's a chain of blocks. So it's like a linked list, if you're familiar with that data structure. You can keep that apple. Or you can donate it to anyone. Okay, so difference between centralized and decentralized. So we are all familiar with this probably when there's information sitting on a web server somewhere centrally. In our case of apples, I could just, if I'm the admin here, I could just fake this and say I have 100 apples. That's bad. With this, that was the scenario that I mentioned, if every single person has a copy of the current state of what's going on. And faking this here, as I mentioned, is kind of hard because they all say, no, this is wrong and this is wrong. Yeah, this is a very simple, basic explanation of this. It can get much more complicated than this, but I hope that makes sense so that we can move on together to the next things. Next thing, Ethereum and smart contracts. So Ethereum has something that's called smart contracts. Other blockchain projects also have this, so it's not Ethereum specific. The idea behind this, basically a smart contract is just a bunch of functions that allows you to either write to the blockchain or retrieve information from a blockchain. Some people compare this to a vending machine. So let's say you give someone 100 yen and you get something back, Coca-Cola or whatever. So what it does is as I said, it's a set of functions. You could think about it as a class with a bunch of functions in there. And those functions do something. So they either read from the blockchain. Let's say you have one apple. This could be a call to a smart contract. Or also our trade could be a smart contract. I give you an apple and you give it back to me. Maybe give me money or whatever in exchange. What's interesting to note is that those smart contracts can't be changed once they sit on the blockchain. So basically, they have an address, a fixed address on the blockchain. So whoever has a wallet has an address, basically, and also a smart contract has an address similar to a wallet, and then you basically call to that address. But we're gonna go deeper into this later. This is just touched the surface. So I hope that makes a little more sense now. Ethereum is a decentralized platform that runs smart contracts. And all the other stuff, this is because it's decentralized, distributed in that sense. Yeah, censorship, we talked about in the case of Turkey, Tsubasa. Thanks for that picture. Third-party interference and so on. So, okay, so now let's write a smart contract. How do we do that? We use the language called Solidity. Solidity was created by the guys behind Ethereum. It is a language specifically designed to write smart contracts for the Ethereum blockchain. This is the syntax, how it looks like. So, three things I want to highlight here. It is a contract-oriented language. Sounds familiar. So you could also think object-oriented language, whatever. You have a bunch of contracts. They're like classes. Actually, I'm going to go like this. Yeah, so they are basically classes you can inherit from other contracts. You import it first, and then you can inherit from that. It is statically typed, which basically means you have to declare the type of a variable once you declare it. Coming from the JavaScript world, structs was a little new to me, but other languages have this. So basically here a struct, this is how you write it. This is basically an array of a type called zombie in there. So this is from a tutorial called Crypto Zombies down here. That is a really, really good introduction to writing smart contracts with Solidity. In the last slide, I have a bunch of resources that you can check out. And this is how you do a mapping. So in that case, you map in IDs, which is an unsigned integer. This is what int stands for. To an address. An address is baked into Solidity. It's basically a hash of your address of your wallet, basically. Something to note also here, you have public and you have something called internal. Public means you can access this from outside of the smart contract. So you call it and you get the information back. Internal means you can only access it or call it from inside the smart contract. There's also something called private. There's a slight difference there. And there's also something called external, which means I can only call it from outside of the smart contract. This is how you declare functions. The variables that it takes, you also have to define what types there are. But we're going to write our own smart contract in a second. So you will see this again. Let's build our first decentralized app. Okay, so Felix, by the way, there's no timer. So we are on a coding school called Chrysalis. So I thought, okay, it'd be cool to have an alternative coding school that is online and on the blockchain called Hack Butterfly. This is what we're going to build. And the idea with this, so I thought about, okay, what could be an interesting application for decentralized application. And I thought about something like that you could refer to as a transparency standard. So let's just imagine a scenario you're interviewing a candidate and this person went to Stanford. And something seems a little fishy about this person, so you have to background check this person a little bit. So you basically call up your friends at Stanford or a professor or some other people that went there at that class to really verify that this person went there. That takes a bunch of phone calls, could take some time. That sign up to this program, sending Ethereum, so you pay, sending Ether, so you pay with Ether, which is the currency of Ethereum, and then you're enrolled. And then once you're done with all the requirements, the school here can then turn your status from enrolled to graduated. So that's the idea. And by the way, this is where the ownable class comes from, because the school basically, if the school deploys a smart contract, the school is the owner with its address, and then only the school can call certain functions on the blockchain. So there's some security that you could bake in there, but I'm not going to go too deep into this. Okay, how would you go about building this stuff? In a centralized way, what you would have is a central server. Let's say it's a relational database with all your tables in there and all your students and the status. There's an API that basically connects the database to your front end, and you would have just a simple front end. I think most people have done this here. How would you go about the central world? So you have the blockchain, which serves as your backend. So there is no database. It's your blockchain. And there are smart contracts that basically either read from that blockchain or can write to that blockchain. Basically, change the state of the blockchain based on the interactions that your users have or your students. And then you need a front end, so that part didn't change. And there's something in between here that allows you to talk from the front end to the smart contracts. That's basically an API that we're going to talk about in a second, which is now. So for the blockchain part, we chose Solidity, we chose Ethereum as our stack. For smart contracts, we do Solidity, and then this is this API that I mentioned. So this lives in here. So this allows the front end to talk to the smart contract, basically. And I chose Vue.js for my front end. It is a JavaScript front end framework, similar to React. I personally like Vue more than React, but that's just taste. We're not gonna do much with Vue. So if you're not familiar with it, don't worry. That's fine. Oh, by the way, I took those screenshots from another project called List. They have a really good academy, by the way, if you want to get deeper into this. Okay, so first, we're gonna do the blockchain part. What do you think we have to do? Right, nothing. It's there. You don't have to touch it at all. It's already there. That's great. It's public. You can use it. So the next step is we have to write our smart contracts in Solidity. So let's do that. I'm just going to put that here. So this is how you write smart contracts. I'm going to go first. This could be overwhelming, but so bear with me. This is something called Remix. It is also built from the guys at Ethereum. It's an IDE that lives in the browser. And you basically write Solidity files with this. So on the left side, you see all your files here. In our case, we have the Hack Butterfly demo, which is this here. It comes in with a ballot and ballot test, and there's some other stuff that I did also. But anyways, you don't have to look into this here. .sol is the ending for Solidity files. And on the right side, there is your compiler, where you can compile your code and check it. There's something called run. So when you click here, there's a bunch of stuff. So it's starting at the top. There's your environment. What's the environment you're at? So it says you have a bunch of options. You have the JavaScript virtual machine, but what we look at is injected Web3. And what is injected Web3? So Web3 gets injected by something that's called MetaMask. And what MetaMask is, as you see here, it's basically, so it is a Chrome extension that you can install on Chrome. And it is a wallet that stores your Ether. And you can send transactions with this. You can send transactions, you can deposit more Ether in there. And what's most interesting here is that it injects a Web3 instance in your window. So it basically has a little script that injects Web3 in there. That's why it's called injected Web3. This is MetaMask. I really like this. I don't know why. This is how you get it. Yeah, I don't know. I could do this all day. Anyways, so this is your account. And then this is your account, which is with a hash and how much Ether you have. So in our case, we now have 10 Ether, which is today about 3,200 USD. Don't worry, it is on the test net, so this is not my real money. So there's a bunch of networks here. There's the main net, which then it would be real money, and everyone could use it with real money. There's testnet that we want to use for testing purposes. We don't want to test stuff on the mainnet, never ever. Then you see on the right we're on the Robson testnet, so this also shows where we are. There's something called gas limits. So gas is basically a fee that you have with every single transaction. And it's a tiny amount of ether that you pay with every single transaction, basically. And then you have value. So in this case, value is how much money, how much ether you sent with your transaction. On the right side, you see something called VEI. VEI is just a smaller, much smaller unit of ether, basically. So ether shows this here. And how small this is, I want to show you here. This is 1 ether, and this is VEI in 1 ether. So 5 ether is a lot of VEI. Okay, just keep this in mind. We will get back to this later. Okay, so I hope this makes a little sense, this whole thing here. Let's build our first smart contract. So in the beginning, we have to declare what version of Solidity we use, and then there's something called pragma. You just write it there, basically. So pragma, Solidity, and then the version. It's always there. Then we have our contract. We call this Hack Butterfly. First of all, we want to say how much money really our program costs. So we have an unsigned integer that is called program cost that we set to 5 ether. Ether is baked into Solidity because it's the currency of Ethereum. Like, makes sense to give it a, yeah, it's not a variable. Student, so we want a struct called student. So how do we create our student here? So we have a struct called student. And what information do we want here? So let's say we want the age. And age could be an unsigned integer of 8-bit because people don't get that old. Say age. Then we have a string of first name. So we do first name. Then we have a string of last name. And what we want last is status. So we're going to choose to have a string with status. It's either enrolled or alumni, so we could technically also take Boolean here. But what if someone drops out? Or what if there's another status that we want to add later? So let's do it with a string. Once the student is created, the student should live in an array. We want to look them up, right? So how do we create an array? It is an array that is of the type student. Student. And this is going to be public, which means I can access this information from outside of the blockchain. And this is going to be called student accounts. This is my array. And then second, when I type in the ID of the student, I want to see the address of that student. So we're going to do a mapping here, where we map an unsigned integer, which is going to be the ID of the student, to an address. An address is a type that is also basically Solidity specific. Address is the hash and the address of your wallet, basically. That's going to be public because I wanted to access it publicly, and let's call it students. Yeah, by the way, I wrote some pseudocode up here, so that's easier to follow, also for me. Next, we're going to declare a function. So this is going to be the heart of our decentralized app. We want people to enroll into our program. The way we do this, we're going to declare a function that we're going to call enroll student, and it takes a variable age, so it's an unsigned integer, 8-bit, called age. You see this underscore that I took this from the Crypto Zombies tutorial. So basically variables you want to declare with an underscore in there, and then string with first name, and then we have a string with a last name. And now it's getting interesting because we want to make money with this. So this is external now, so people can call it from outside of the smart contract. And there's something called payable. And payable means that you send a value with this. You send ether with this. You pay, basically. It's a pay transaction. This is all it takes to basically enable people to pay me money. So whoever set up already a payment system in like standard full stack app, or maybe use Stripe, this is even easier. It's just one word, payable, which makes you to accept money. Okay, so next we want to first check if this person actually sent the money, the cost of the program. So what we do is something that's called require. So this is like an if statement, and it says from the message that someone sends, and a message is the transaction basically. So we do message dot value, and value is this here. And this has to be our program cost. So we have program costs. Remember up here we declared program cost to be 5 ether. So if this person has sent 5 ether with the transaction, we continue. If not, this function gets canceled, transaction gets reverted, nothing string right away that says it's enrolled. Okay, so now our student exists now. We want to put this now in the array of student accounts. So the way to do this, similar to JavaScript, and you're going to do students accounts dot push, and then you push it into the array. And if you also come from the JavaScript world, as I do, actually, wait, we want to first get an ID of the student. So unsigned integer called ID, yeah, which is student's account. So when you push something into an array, it returns you the length of the array afterwards from there. So ID in our case, if it's the first student, is 1, but we want to start counting at 0. So we want to do -1 here, and this should start with a 0 then with the first student. Okay, good. So what do we need next? Next we have this mapping up here. So what we want to do is we're going to do students and just put in our ID in here, and at that ID, so it's the first student again, it's going to be student 0. That's going to be message.sender. And message.sender is basically the address of the person that sent this transaction. That's all. This is our whole enroll function. There's a little helper function that I have down here that we don't really need, but I figured it would be interesting for learning purposes. This is going to return the total amount of students that we have in our school. So it's a function that's called getTotalStudents, which doesn't take anything. And in Solidity, you also have to declare what it returns. So you type in returns an unsigned integer. Unsigned integer. And I think you do public in here. So this is public as well, and only view. And view is a new thing here. What it does, it says I just read from the blockchain. I don't write to it, I don't change the status, I just read from it. And what all it does, it just returns the length of our array. So this is going to be student accounts dot length. Okay, that's all. So this is a very simple MVP of our smart contract. We're going to check out the compiler if we've done any mistakes. So let's see. There is a mistake, so let's see what it has. So these error messages are actually kind of useful. And by the way, also, if you check out the documentation of Solidity, versions change really, really quickly. So in the documentation, something could be outdated, but I found while I built this that Remix, those little tooltips here are the most up-to-date. So there could be mistakes in the documentation still. So you want to, rely on this. And it doesn't return, it returns a return. Yeah, and there's some other stuff here. What do we have? First name, last name. Did I mess something up on here? Say it, can you sound?
The underscore is missing in the argument.
Oh, thank you guys. See, this is why you do underscores in your variables. I guess. Wait, last name. Wait, what is it? Oh, sorry. It's done, compiled. So compiler's green, good, thank you guys. So it compiled, looks good. And now we are going to deploy the smart contract on the Robson test network. So what to do here is we have our account up here, and we're not going to send any value with this because we don't need to send value with this yet, because all we do is make money. We don't pay anyone yet. So we're going to deploy this here. So we click on deploy, and then it creates this window, which is our friend MetaMask. So this guy causes this window to pop up, and we have this gas fee. I hope you can read this. You can make this big. Yeah. So the gas price, we're going to increase this right now. So if you increase this, the transaction just goes through quicker, which means the miners just pick it up earlier, and then it just goes quicker through the network. Since it's plain money anyways, we're just going to increase this because we don't want to wait. I'm going to confirm this transaction, and this now writes to the Ethereum blockchain. You see this here? This is a link that we got. It brings us to a website called Etherscan. So who's not familiar with this? Basically, this is a website that shows all transactions that are going on Ethereum, on the Ethereum blockchain. You see here, this is the Robson testnet. I can make this a little bigger. This is our transaction hash, and it sees from who it's sent and to whom. And since it's a contract creation, we don't send it to anyone, we just send it to the blockchain. And it gets basically right now sent here. What you can also do up there, when you can analyze certain other distributed apps. So see basically who's interacting with this distributed app. So in the case of CryptoKitties earlier, you can literally see the transaction that is happening to this CryptoKitties decentralized app and who's using it with how much money and all that stuff. I can show this to you later. Let's see how this. Okay, this is very slow. As you can see, the speed of transaction is really slow. I'm gonna show you the CryptoKitty smart contract now. Smart contract. So as you can see, this is what I mentioned earlier. You can literally see the smart contract here from CryptoKitties and the amount of transactions that are coming in and out and how much was sent there. And whoever is new to this, doesn't really say much. So ERC20 tokens is basically Ether, or some other tokens on the Ethereum blockchain if you start the project. So most ICOs are ERC20 tokens. ERC721 are the collectibles, so they're unique. This is a whole other lecture on another day. But what's interesting here is that they show you the code of their smart contract. So what we just wrote, you can see that from the CryptoKitties guys. I can scroll down here, there's a bunch of stuff. So you see there's a cooldowns here that they declared and all sorts of things. So if you're interested, you can check this out. This is what I meant with transparency. So when you call the smart contract in the CryptoKitties game, you know exactly what you're getting into because the smart contract is there. I hope this is done now. Yeah, okay, that took a while. So our transaction is done. Our contract was created, so let's click on this. So now this is our contract address up here. It's big enough. I'll zoom in. And there's a balance of 0 Ether because no one has paid us yet. Okay, so this is now sitting here. Let's interact with our first smart contract. So this has been confirmed. It is down here now. So I can see get total students. How many students do we have? 0. Okay, that's obvious. Let's sign up. So let's say we want to send 5 Ether and enroll a student. Let's enroll myself. So I'm 26. First name is Michael. Last name is Arnold. And let's enroll myself. So it opens up a transaction window here again. This time, however, you see there's a bunch of money that is attached to this. It's big enough. This is 5 Ether and our gas fee. I'm gonna this zoom is a little weird. Let's increase this again and save this and confirm this. And let's hope that this gets through a little quicker this time. When we click here, so you see now it's sent again from my wallet address, from my hash, to the smart contract. And as you can see here, the value is 5 Ether. So we're sending 5 Ether with that transaction to the smart contract, basically. And yeah, this is a transaction hash, same as the one up here. And we could now wait for this to finish. What I could also show you guys is let's just oh, it's done. Okay, let's refresh this. Okay, so this has been done now. This is the little tick here, and this is our contract. And our contract now has 5 Ether sitting in the contract. So now we made our first money. We could, if you were the school, then also get that money out of the contract through a function that is only called by the owner. This is where this comes in handy. But yeah, so now we check out the students here. So we have now 1 student. And if we check out the student's account, so we said that we start counting at 0. So let's do this. And it returns us Michael Arnold, enrolled 26. So this information sits now on the Ethereum testnet. And we now deployed our first smart contract. And it works, and the information's in there. Okay, so Solidity, we've looked into this, we deployed our first smart contract. So this is done now. What's missing now of this whole full stack decentralized app are 2 things. Basically the front end. And the front end with the Ethereum API to call functions through our front end on the smart contract. Solidity has been the main part here. So the front end stuff is going to be very quick and short. So bear with me. This is how we basically put all the pieces together now. Okay, let's look into Vue and Web3 and what that all is. This is Visual Studio Code. Probably seen that now, also with the other students. And this is a simple Vue project. Don't worry too much about it. There are components. So the idea of React and Vue is that you have your whole front end in several components that you have. This is just simple HTML here and some styling. Don't worry about this. Worry about this stuff. But before we dive into this, I want to show you the final product. So this is how the front end looks like. So the code that we just saw, that's the front end. It's live on Heroku. You can check it out. If you have money, you can sign up with test money, not real money. Yeah, so you have your first name, last name, age, and your students here, and alumni. So I've added some alumni stuff. Yan Fan is one of our alumni, so the school has to be good. So yeah, so I added a little bit of bunch of stuff that the school, as I said, can then turn a student into alumni once it's done. Oh, it's not getting too fast. And then I have this instance here. And there's two things that we can get. So if I jump back, what you see up here, my address and my balance, the way to get that data is this here. So this is a simple promise that we have with async and await. And what we do is we're going to do web3.eth, stands for Ethereum, and then you do a function or a method called get Coinbase. And this is how you grab your address, your Coinbase basically. The next one is get balance from a specific address. So we save that Coinbase here first, and then we grab that balance basically from that user. And remember when I mentioned Vey and Ether, so it gives you the data in Vey, this really, really small unit of Ether. So we divide this by this, and then we get back the Ether unit. Okay, now, how do we get the contract? How do we get the initiate a new contract instance? And this is where it gets interesting. So what we do is here we create a new instance of Web3, so new Web3 ETH called contract. So this is we just create a new contract instance from that smart contract that we created, and it takes a few variables back here. So the first one is called ABI. That stands for Application Binary Interface. It's written here. It sounds more fancy than it actually is. All it really is a bunch of instructions how to interact with that contract. So this is an example of an ABI. You see here enroll student, it's payable, it's true. Can you mutate the state? Yeah, it's payable. And yeah, a bunch of other stuff, graduate student and so on. So don't worry about this. If you want to do it yourself, where you get this from, remember we go back to Remix, and you go to this compiler tab and you go to details. And then this details spits you out the ABI. You just copy paste and then you have it. So very straightforward. And then you get the contract address. So remember before I showed you on Etherscan our contract address. In our case, I saved it here, this hash. It's a different one now because it's the one that I updated with a bunch more stuff. And this is optional, the stuff here in the yellow curlies. This is a default gas price that we set with our transaction, and the next one is a default address from this is going to send from, which is the address that we grabbed, and we just set it to 5 because we just want to be quicker. You can also just leave this out if you want it. And yeah, and then we have our contract, which sits as hack butterfly contract. Yeah, this is Vue specific. I don't want to get into this, but now let's say we want to grab all the students that we have. So how do we do that? How do we go about that? This is a method that is also asynchronous. That's going to be called total students. That's going to be the result of it. It's a promise again. The way to do this is that you grab that contract instance that we just created, basically, and then do dot methods. And then if you do dot methods and you console log this, you see all those different methods and functions in your smart contract. So then you just grab the one that you want, which in our case is get total students, and you shouldn't forget this thing. So you have to call this. So this is how you call that function in your smart contract. That's all. As easy as that. So you grab this, it's a promise, so you wait your promise, and then you have your students. And once you have the amount of students, you then go through the array of students, and for every single student, basically, you grab that data. This is what the next lines of code do. So there's another one called getStudent, which is defined down here in line 93. And then what it does, it calls the function called studentAccounts with the ID that we have, and the ID is from the loop that we have here, and then also calls it. So this is, if you now jump back, this is how you get all the students here. And then there's some logic. Basically, we have two different arrays. It's either student array, so if it's enrolled, we push it into students. If it's graduate, we push it into alumni. That's literally all it does. And now let's look at this thing here. Let's look at how to sign up and actually send money. It is a little different, but actually similar. So this is the enroll component. And I just want you to look at this here. So line 106. Don't worry about this if statement. So all that does is it checks if this has been checked. It's not the safest way to check if all the information is in there, but let's just live with that for now. Okay, so we have our contract instance. We do methods, similar to what we've done before. Then we enroll the student with all that stuff here. So if you remember, in Remix, our enrolled student function takes an age, first name, last name. So we pass in now the age, first name, and last name that we get through the sign-up form. And then instead of call that we saw in the previous examples, we do .send, because it actually sends money, that sends value to the smart contract. And what it sends, it's basically the program cost that you defined earlier, so the 5 Ether. Yeah, and then we await this, and done. And then we have a student. So this is how you enroll and do that. We could do this here right now. So Michael is actually still missing down here. So let's do Michael. Arnold, still 26. Yes, it's correct. Same stuff. So we grab now the MetaMask, and this creates this MetaMask transaction. And we see now in this edit, this is already at 5 because we set the default to 5. And we're gonna confirm this transaction. And now it's send off the way how we see this. So there could be some front end nice stuff here to see a spinner, which I haven't done. But you see the transaction here. So this is submitted instead of confirmed. So we click here, and this is the thing that we already saw. That this is not new to us. Yeah, so the pending transaction could take a while, so I'm not gonna wait now for this. We've seen this. And it works, yeah. And once this is done, when I refresh this, Michael Arnold is also down here. We can come back to this later. I'm not gonna spend time now on waiting. Okay, so this has been the front end. Hope it wasn't too rushed. It's been a lot. So let's just quickly recap before we finish this whole thing. First of all, what we have to do is we build our smart contract in Solidity, and we use Remix as our IDE and to deploy that smart contract to the blockchain. As I said, with deploying Remix and something called Etherscan, there we see our transactions, and we see basically some bunch of other interesting stuff. So if you're interested there, actually check out Etherscan and really dive into this. It's really interesting. Then we have to connect it to our front end, and we use Web3 and something called ABI and our address of the contract. And lastly, to interact with our decentralized apps, we use MetaMask. There's some other examples, other tools you can use. I chose MetaMask, which is this injected Web3 that I talked about. And that's all. This is how you build your full stack decentralized app. Summary. So we talked about data, transparency, trust. We talked about apples. We talked about centralized versus decentralized and smart contracts, and full stack decentralized app. If you want to get started yourself, this is what helped me reading this. So I had like a high level surface idea of blockchain crypto stuff, but mostly from the business side of things. So I started, I would say, a month ago to dive into the tech side of things. So this really helped me to learn all that. All those links you can find on my repository. That repository is the code base of what you just saw. So if you are familiar with Vue, this is a really, really good boilerplate to get started. This README here contains a bunch of information I talked about, the MetaMask plugin, how to get test money for your Robston wallet, basically. There's some introduction stuff, some useful links. And lastly, the links that I mentioned here, crypto zombies and whatnot, and some interesting projects. If you're interested to learn more about this, check those projects out. So the first one, it's called Truffle. Every serious smart contract, or most serious smart contract developers actually use Truffle, which is like a whole suite of tools that also give you unit tests, so you can write real unit tests for your smart contracts. It also comes with its own blockchain to test stuff, so you don't have to do it on the Robson testnet. Could be a little longer, because you saw the transaction that took a while. If you do a bunch of stuff every day, it's going to get very, very slow. Yeah, this is the link here, and that's it from me. Thank you very much. Questions, suggestions, ideas? Yeah.
Can you show us if the transaction's been mined?
Oh, good question. Thank you. Success. I think that was this one. We can prove it now. So Michael is missing here. Let's refresh this. I think it should definitely be through. I would be very worried. Okay, so students. So as you can see, getting the data is really slow. So talking about efficiency, a blockchain is like, it's not the strength of the blockchain to make something efficient. So Michael's here. Thank you for the question. Good question. Any other questions? Yeah.
These, like getting the students, the number of students, you didn't pay any either.
Yeah.
This is run locally then?
No. The way we do this, it goes back to here. So it sends a call to the blockchain, and I just read from the state of the current blockchain. So it's not done locally. It is a function call that gets sent to the blockchain and then gives me information back. But since we're not writing to the blockchain, we're not changing the state of the blockchain, it doesn't cost us any ether. So we just read from it. It's like,
but this function could be like super long, computation.
You mean that if you just do a really, really long reading function, it could just make things inefficient? Is that what you're saying? Yeah. So when you, how do I go from there?
You could have code in there that does
that just runs forever.
That's some long computation that
Yeah,
you don't want to spend.
that's a good question. I haven't tried to break it really. So there's something. It could also be that when you read only from the blockchain, you also don't pay. Hold on. You pay, but if you do pay gas, then if it's a long function, then you would just pay more gas, and then it just would even it out. Because then you don't have an incentive to basically call this long function.
Just runs on your local instance, because you're just reading.
The thing is, you don't host the blockchain. You don't. So when you come from IPFS, you would think, when you consume this, you become a host yourself. You become a node yourself. But not in this case. So I'm not a node of the distributed network. If I were, the blockchain is really huge. I think right now the Ethereum blockchain has information of 1 terabyte or more. So if you can't give this to your users, right? So everyone with I could not do this on this machine. So yeah, the idea, you don't become a host. So basically you take it from the closest node, let's say, the information. I hope that clarifies a few things. Yeah, but I need to check if you actually pay gas. Do you know, Dylan?
Yes, I know.
Okay.
And you don't pay gas. Reading does not cost anything.
So how do you solve this if you have a long function?
So you guys are both right. It's actually supposed to run the way IPFS runs.
Okay.
But since Ethereum is such a big network, you're just using someone else's node that's hosted in the cloud, and they're essentially running the operation locally, just reading the information for you and sending it back.
So if you have a really long function, you have a bunch of computing power that you consume?
It's not run on every other node. So you only have to pay for a function that all nodes have to run.
Okay.
Call is a function that only runs on your single node locally, and yours
Okay.
sharing the data.
And you can do this because you can trust that all the nodes have the same information?
Yeah, they're up to date.
Okay. Cool, thank you. Great.
Guaranteed.
Thank you. Thank you. Other questions? All right.
I've got a question.
Yes, please.
How did you? So you said that you didn't know anything on the tech side for blockchain before you started.
That is correct.
How long did it take you to create this demo?
I would say about 2 weekends and a bunch of evenings. So what was really helpful, okay, this is gone. What was really helpful was the Crypto Zombies tutorial. So everyone who wants to get started with Solidity, check out the Crypto Zombies tutorial. It lets you build a game in a very playful way, unintended, and just learns the syntax of Solidity. So that was really good. And since I like Vue, I was Googling for a full stack decentralized app written in Vue and Solidity, and just basically follow that tutorial. And then with this information, I thought, okay, how can I build this differently? And then I built this decentralized coding school. And I feel like for me personally, taking something and then building my own thing out of it and then breaking it is a good way to learn about a new thing. So yeah, 2 weekends and a bunch of evenings and frustrations.
Cool. Same question to you, Hiro. How long did you know anything about Dijkstra or pathfinding algorithms before? No?
No, at this time. So maybe, I don't know, same as Michael, 2 weekends, maybe. Yeah.
2 weekends, sweet. And same question to you, Tsubasa.
Yeah, well, I think it was like 1 month ago where I was just like thinking of an idea of like what to do, what to learn, and then Dylan was like, "Bro, this is a cool technology. Bro, you're right." Yeah, and then it was actually 2-3 weekends. Yeah,
Not
that's
bad.
my actual.
Cool.
Yes,
And
thanks.
thanks.
Yeah, to add to this, it's really, really easy to get started with smart contracts. But when you really want to build something that is robust and safe, that is deployed on a mainnet, that's a whole different story. That's really hard. So, yeah, that Dylan, I think you mentioned it once. You would never ever deploy a smart contract to the mainnet.
It just seems scary.
Sweet. Well, yeah, they're 2 months into this 3-month course. So we usually do this about 2/3 of the way through. So the students actually chose these topics on their own. We had as instructors, we had very little to do with this. But I do want to thank Dylan right there, if you can raise your hand. Yeah. So Dylan's one of our instructors, and then Felix hanging out back there. So we absolutely would not have been able to do this without these two. And Felix has been dealing with our very hacky, startup-y live streaming system. So this is all live streamed right now. Thank you, Felix. This is all live streamed right now on YouTube, Facebook, and so if you guys missed one of the talks or whatnot, you can go find it there. Thanks for coming to Big MiniConf. This is it, guys. We will be doing another one around November, which is when our next batch of students are going to come. We don't know what the topics will be yet, so keep an eye out for that. A few things. Before you leave, we want to take a group photo with all the people in attendance, so please be in that photo with us. Yeah. Another one is please throw away anything that you might have used. Just help us clean up a little bit. We love doing these free events. That's something that was, one of our core missions here. There's so many tech events that charge a lot of money, and so we really wanted to create an event that was free and also welcoming to first-time speakers and also people who are new to the industry. So another thing, if you're interested in Code Chrysalis, Connie right there, who's the other co-founder and our CEO, and we're happy to answer any questions that you have about the program. We've got a bunch of events coming up. So these are the events that we have in the next 30 days. And we have more that are going to be put on here. I'm leading an Intro to Programming and JavaScript workshop on Wednesday. That's free. All of these events are free, actually. So please come. Real quick, our current batch of students, Hiro, where are you all? Dustin, Kimiko, there you are. And then Tsubasa, Michael, who you just heard from, and Tsuyoshi. Am I missing anyone else? All right, well, they will be, and Noor, they will be graduating on September 27th, so please come to their demo day and check out what they have built. what else? We would like to also thank GitHub for sponsoring if you are interested in sponsoring a future big MiniConf or demo day or whatnot, please reach out. We're always happy to have more free pizza. And of course to make friends. Let's see, what else? What else am I forgetting to say? Oh yeah, please come to Battle of the Blockchains. I will be talking about something blockchain related there. To be determined topic. It'll be, I'm sure, fantastic. And please follow us on the social media things. The deadline to enter our next immersive is next week. So if you're interested, please apply. You can see the quality of our graduates. I'm sure they're happy to, our current students are happy to talk about their experience. I hope it's been good so far for them. And Connie, any parting words? Anything that I've missed?
Thanks guys for coming. I think without you guys this won't be possible. Let us know after this if there's any ways we can improve it. This is our first big MiniConf, so I would love to hear even now if you have any ideas, thoughts, suggestions, feedback. Please, without your input we can't make this any better. But we think it's a big success. We didn't think we'll have this much people for 2 days, and it's been great. So thank you.